record. There we go. This class will get recorded. You'll get a recording of it probably tomorrow. It takes a few hours for everything to process afterwards. If you need a certificate of completion for your boss to get reimbursed for something, you'll get an email after you take this class. There'll be a short um, quiz, I guess, like 3 questions. Like all you have to do is essentially be alive and have a pulse through this class, and you'll have no problem answering those 3 questions. It just prevents anybody who like did not attend from, being able to say they completed it. There are no CEUs for it. I'm not that important yet, but if your boss needs like proof that you took a class, you can get a certificate if you need it. If not, there's really no other purpose for having the certificate. Let's see, you'll get the recording. Yeah, so what we'll do is we'll go over some training for the next 2.5 hours or so. We'll take some breaks, and then we'll hear from Nikki. She'll be talking to us about some of the new stuff Santa Fe Dehumidifiers has got going on. Then we'll close with some a couple slides at the very end, and then afterwards, so around 9 o'clock, what I do is for anybody that wants to stay on, we can have more of a question and answer session then. I call it happy hour because by that point I'm wore out and I go to the refrigerator and grab a beer. And then we tell some war stories. We ask questions like whatever for, an hour or so if we need to. So if you want to stick around for that, it's a great time to learn. But I'm going to go ahead and share my screen. If we could do a mute all, that way if anybody, has got some background noise, it doesn't disturb. So we will, oops, sorry about that. All right. Yeah, so yeah, if you as new people come in, Nikki, you just make sure that they're muted. Um, but I appreciate it. All right, I'm gonna share my screen here. This is Manual S simplified. Um, Let me move this window over here and okay. So everybody, if I can get a thumbs up, everyone can see Manual S simplified presented by Santa Fe. Awesome. All right, a little bit of information about me. Probably you found me on social media, so these are my social media handles. My company is Comfort Science Solutions, and then I also encourage you to look up betterhvac.org. It's sort of an aggregate of all the HVAC organizations and professionals out there that are doing good work. You can build a profile as an individual professional, so you don't even have to be like a company or an owner. You as a professional, as a practitioner, can take a pledge to do better HVAC, ethical sales, science and data-based recommendations, just the good ethical stuff that we talk about. And people can find you. And if you are a company owner, there's a place to put that profile on there as well. But if you think about like a homeowner or a customer that's just looking to, just desperate to find somebody that's not going to rip them off, that's going to do a good job for them, where do they go? There's a few places here and there, but none of those are a total list of the good HVAC professionals around the country. We're trying to make better HVAC that place. Um, all right, here's our learning objectives for the day. We'll talk about what is Manual S, and of course, that's sizing and selection of HVAC equipment. We'll cover furnaces, air conditionings, and heat pumps in a variety of climates, because it does change a little bit. We'll talk about when you put in supplementary and emergency strip heat and how you size them, heat pump balance points, supplemental dehumidification. And then we'll hear from Nikki about some exciting new stuff with Santa Fe. Um, Here's where I get my training from. Hopefully, you know some of these people, some of these organizations. NCI, National Comfort Institute. It's a great organization for training as a contractor for testing, airflow testing. They're big on airflow, combustion, and total delivery capacity and diagnosing units, and that's what I'm about too. So I get a lot of my training from them. Obviously, HVAC School and Brian Orr, their tech tips, their videos, a ton of content there. That changed my life as a professional when I started consuming that. Alex Meany, Mean HVAC, he's a trainer, used to work for Wrightsoft. He knows a ton about HVAC design and building science. The great people at ACCA, they're the ones that make Manual J, Manual S, Manual D. Ed Jonawak is one of them. He's got some great videos and great teaching content out there. And then Dr. Allison Bales, Energy Vanguard, he wrote the book A House Needs to Breathe or Does It? This is your introduction to high performance HVAC and home performance. It's written in a really easy manner, and it's how you can kind of get started with those concepts of how to just understand the building as a system. So the ACCA design process, this is the steps that we take in HVAC design. It's got to start with the manual J, residential load calculation. That's your heat loss and gain for the building. Now, manual J does not tell you what size equipment needs to go in for that load. That's what manual S is all about. It's residential equipment selection. That's what the S stands for. All right, so essentially we're matching our equipment to the load. The manual D, of course, is our duct design. And so this is sort of the order that you would take when you're designing a job is you do the heat load calculation, you figure out what the building needs, then you find equipment that will match it, and then you build the duct system around what that equipment can do. This came from ACCA. This is their manual LLH, low load homes. We sort of laugh at the fact that some contractors stand at the edge of the road and they hold their fingers out to the house. And if you can cover the house with one finger, two fingers, a 3 ton, it's a 2 ton, 3 ton, 4 ton. And that's how they size units. And we laugh at that. But over the years, they've collected a lot of data. And this is the people at ACCA that make Manual J. This is what the data says that, you do have a range of square footage from houses that are built within a certain time period. That's sort of how it works out. Doesn't mean you've got to skip the Manual J and the Manual S. It just means that we have learned a few things along the way. Now, there is still a pretty big range. You're talking about 400 square feet per ton that you could be off. So we don't want you to use this, but we do want you to know that, like, there are some patterns that we've learned as an industry over the years. What we're going to do is learn the right way of doing it. And that way, when you start seeing those patterns in your jobs, then you may be able to not cut some corners, but save some steps. So I'll give you an example. When in Greensboro, North Carolina, which was my old market, I could eventually go up to a house that was built in the 80s. That was a 1,500 square foot ranch, and I knew that a 2.5 to 3 ton unit was going to go in there. I didn't have to do a load calculation every time. But that's only because I had done hundreds, if not thousands, of load calculations before then, and I earned the ability to, if everything kind of looks pretty normal, I kind of know what's going to go in here. But we don't get to do that until we've done the work, we've done the reps. And then at that point, maybe you can start using some ranges. So until then, we really want to do it the right way so that we can learn those patterns. And we're going to do that tonight. So Manual S picks up where Manual J left off. The Manual J, when you got done with your Manual J, if you did it right, you learned a few things about the building. You figured out what the sensible load was. That's your cooling load that's going to change the temperature on your thermostat. Okay, sensible has nothing to do with moisture. It's simply what makes a thermostat go up or down. All right, that's your sensible load. You also quantified your latent load. That's your moisture load. That's how much heat is going to be required in order to remove the right amount of moisture from the building to keep them comfortable. When we add those two together, we come up with our total cooling load. Okay, so sensible plus latent equals total. We also learned what our heating load was, and our heating load is all sensible. There's really not a lot of moisture that we're dealing with in the heating load. Okay, so that's all sensible. So those three things or four things we came away with our Manual J, and that's it. We did not come away with any kind of equipment size yet. Okay, that's where we have to start now. Um, let's see. Our Manual S equipment selection. Here's where some of the pitfalls happen. We know what happens when we oversize an air conditioning unit, right? Maybe somebody can unmute and just say what kind of problems happen when we oversize a system. Feel free to unmute and just say it.
Short cycling.
Short cycling. What else happens when we oversize equipment?
Humidity. No humidity. Humidity. It doesn't pull the
Yeah,
humidity out.
poor humidity
Comfort
control,
issues.
right? What was that, Ralph?
Humidity, comfort issues.
Yeah, comfort issues also, because and so when we short cycle equipment, are we reducing the life of the equipment as well? Yeah, the worst thing that an air conditioning unit could do is turn itself on. The best thing it can do is stay running once it starts. All right. So oversizing, short cycling, that happens when we have too much capacity for load. So the output of HVAC equipment is what we call capacity. You can think of output and capacity as two terms that are interchangeable. Okay. And then of course the load is what we need out of it. And then other problems with oversizing is high humidity, poor temperature control. The unit turns on, it blasts a bunch of air into the house. Let's say it's cooling season. We blast a bunch of cold air into the house. Everybody feels drafty, they feel cold. The unit shuts off, but all the walls and the furniture are still hot. So we get hot like almost immediately as soon as it turns off. Then it's right back to it. So that's not very comfortable. Reduces equipment life. It wastes energy because you get those inrush amps for the first few minutes that any equipment is running. It's not doing a lot of work, and so it wastes energy. On the other extreme, we have undersizing. So what are some of the problems that come when you undersize a unit? Feel free to unmute.
Never satisfy the load.
Yeah, you'll never satisfy the load. You'll never get comfortable in the house on a design day, right? So
Yeah.
that's when our capacity is much less than our load. You guys kind of see the visual here between oversizing and undersizing. Really, what we want is to match the load. We want both of these to be the same size. So yes, poor temperature and humidity control. So then the perfect matchup in a perfect world, our total cooling load comprised of our latent load and our sensible load. And we would find a piece of equipment that matched that with its capacity exactly. All right. Both the sensible and the latent. And then on the heating side, our heating load would be exactly what our cooling load is in BTUs. And that same piece of equipment could just handle the heating load and everything would be perfect. But I've never seen a house or a system that was just like that. All right. So very rare to see. What Manual S does is it recognizes that we don't live in that perfect world. So it gives us guidelines, it gives us bumpers to stay in between. And those bumpers are kind of vary with what kind of equipment we have and what kind of climate that we're in. So that's what we're going to be going over tonight is some of those bumpers. Now, what you're going to realize is that ACA made something that was sort of complicated a lot more complicated. And now my job is to try to take all these options that they opened up in their last revision, and my job is to try to simplify it. And so there's one slide in here, you'll see it probably in the middle, where it says Tim's Simple Rules for Sizing HVAC. And that is like Manual S, that big thick book in one slide. And that's what I think you should take a picture of. That's what you paid for in this class, okay? But we'll get there. We'll talk about some of the principles behind it. So in the real world, this is what happens. We've got a total cooling load. It's comprised of a latent load and a sensible load. And then we've got a unit that, is probably a little bit bigger than the load, you know. Maybe it's a little smaller than the load. We're getting as close as we can with the available sizes, 2 ton, 2.5 ton, 3 ton, 3.5 ton. All right. But then on the heating side, you're going to have a very different heating load than your cooling load. And so then if you selected your unit for cooling, then it might not be the right size for heating. Or you could have like a furnace that gives you more than enough heating, and now you may have more than enough cooling than what you need. So what are the guidelines? Where are the bumpers that we set up to make sure that we're not oversizing or undersizing? So in the real world, the equipment capacity is not going to match the load exactly. All right. And let's think about it. Loads change every day. The sun's up, the sun's down. It's hot, it's cloudy, it's rainy, it's July, it's May, it's October. There's a lot of different variables that go with the load. So, we have to be able to choose equipment that's sort of going to work most days. So Manual S, one of the biggest things we've got to learn about that is something called a sizing factor. And all it is, it's a number with a decimal behind it usually that tells us how oversized or undersized it is. So if the sizing factor is 1.0, that means we're perfectly sized. If it's less than 1.0, that means we're slightly undersized. If it's more than 1.0, like 1.1, that means that we're slightly oversized. And so that sizing factor is the bumper that Manual S gives us. It's going to give us a range of what sizing factor, a number that's below 1.0 and a number that's over 1.0. It's going to give us those two bumpers, and all we need to try to do is stay in between them. So I'll give you an example. The sizing factor, the way they figure it out is they take the capacity or the output of the unit and they divide it by the load. Capacity divided by load is sizing factor. All right. So for example, let's say we have a 2-ton unit. It puts out exactly 2 tons. Its capacity is 24,000 BTUH, BTUs per hour. The load, let's say we did a load calculation and our Manual J said that our total cooling load was 19,000 BTUs. Our capacity divided by our load is our sizing factor. So we would just do this math right here, and we would come up with 1.26. And that means that this unit is 126% of the load. All right. Or it's maybe an easier way, it should say 26% oversized, but it's 1.26 times the load. All right. So is that good? Is that bad? You know, we need sort of some guidance, right, to know whether 1.26 is okay or not. And that's what Manual J is giving us. So Manual J gives us our sizing limit, and that's a minimum or maximum of our allowable sizing factor. So they're saying the lowest you could go is one number, the highest number you can go is this number, and you better be somewhere in between. And so a typical sizing limit for like a single stage air conditioning unit is 0.9 to 1.15. All right. They let you go as high as 1.30 for like a variable speed unit. So typical sizing factor is 0.9 to 1.15. That means you can be 90% of the load. You can actually be like 10% undersized. And Manual J says that's okay. And you can be 115% of the load. You can be 15% oversized. Manual J says that's okay. And if you have a variable speed unit, because we know that variable speed units can turn themselves down, you can be as high as 1.3 sizing factor. So then the question is, our unit right here, it had a sizing factor of 1.26. Is it oversized, undersized, just right? What piece of information did I not give you about this unit that you need to answer that question?
Staging.
Yeah. Is it a single stage, 2-stage, or variable speed? All right. But once you know that, then you know where you are. So really, oops. In this case, let's say that we were a single stage unit. We were 1.15 is our sizing limit for a single stage. We're slightly oversized. So if this was a single stage AC, we would be oversized, and technically we shouldn't use it. All right. We should go down to a 1.5 ton unit, is what Manual S is saying. Or there are some other options that we can do with that 2-ton unit, like slow the blower speed down, that maybe we can get that capacity down within those bumpers. So let's first start with the easy ones. Let's talk about furnaces. All right. And furnaces in cold climates. So we're going to talk about Manual S's bumpers that they put in place for furnaces in cold climates. Here's a screenshot from Manual S, page 26. They're saying output capacity. So we're not talking about the BTU input, we're talking about the output of the furnace. It's either heating only or if it's paired with heating and cooling. They're telling us that the minimum sizing factor is 1.0 and the maximum is 1.4. Now, it makes sense that we would want a minimum sizing factor of 1.0. Our furnace needs to be able to meet the heating load because there's nothing else that will. All right, that makes sense, right? But they're also saying that you really shouldn't oversize a furnace past 1.4. All right, so if your load is like pretty low, Don't just throw in a 120,000 BTU furnace and bust them out of their house. That's not manual S compliant. So let's do a real world example. We got heating only or heating and cooling. All right, so what they're saying is you take your load and you need to be at least 1.0 sizing factor of the load. The maximum is 1.4. Here are your two bumpers. It's sort of like when you go bowling and you got kids with you, and what do? They put the bumpers in there so the kids never get a gutter ball. These are your bumpers, all right? So, as long as you stay in between the bumpers, you're going to be okay. So let's take an example. Our sample load, our manual J, the winter load is 43,000 BTUs or 43.0 MBH. That MBH stands for 1,000 BTUs. It just kind of helps the number stay small so we don't have all these annoying zeros and a comma. So when you see 43.0 or something MBH, just know that that's 1,000. All right. So our load in the wintertime, we came up with 43,000 BTUs in the winter. Let's take a look at one of the furnaces that we're thinking about quoting. We got an 80,000 BTU input, and it's a 96% furnace. Remember, we're looking at the output of that furnace, not the input. So we got to take 96% of 80,000. And when we do that math, we come up with our output of 76.8. So then the question is this furnace okay to put in this job? Well, it needs to be in between these two bumpers. So you got to figure out what your sizing limit is. Your 1.0 sizing factor would be the 43 MBH. Your 1.4 would be 60.2. Does everybody understand how I got the 1.4? 1.4 was what Manual S told us I had the maximum I could be. I multiply that by my load and I come up with 60.2. My furnace needs to be in between these two numbers on the output. And is my furnace in between those two numbers? I got a 76.8 and I need to be in between 43 and 60. My furnace going to be okay? No, I'm seeing people shake their head. Furnace is oversized. Okay. So this is what it looks like. We're outside the bumpers. Everybody kind of understand where we're going with now? All right. So the furnace is oversized. We wouldn't want to put that furnace in there. But you may say, wait a minute, what if I need to put that furnace in there because that's the smallest furnace that will match up with the air conditioning unit that I need? That happens a lot, especially in like southern climates. You have a very low heating load, but you need that furnace to have a 3-ton blower because you're putting in a 3-ton air conditioning unit. And they don't make 3-ton blowers in anything under an 80,000, let's say, for that particular manufacturer. You're like, I have to put in this 80,000 BTU furnace in order for it to carry enough air for my blower, for my cooling. Well, let's talk about warm mixed climates because Manual S addresses that. Notice that it says the output capacity to meet the cooling airflow, or if your heating load is less than 25,000 BTUs. That would apply in most warm climates. You may have a house in South Georgia that its heating load is less than 25,000 BTUs. Do they make furnaces that go down to 25,000 BTUs? Have you seen them? Do they make many of them? No. Like the lowest one you might find is a 40,000. So immediately you're oversized. So let's say that, you still wanted to put a furnace in there and you didn't want to put a heat pump. That's fine. What they're saying is that if you need a furnace to be sized for your cooling airflow, or if your heating airflow is so low that you need to choose the smallest furnace that they make, you're allowed to have a heating size factor of 2.0. Now you're allowed to be twice the size of your heating load. All right. So let's take that same problem here. Here's our load. We're at 43,000 BTUs. And now we're allowed to be twice that. Now they've spread out that bumper a little bit. Now is our furnace compliant? Yeah, it is. So our furnace would not have been compliant in Minnesota, but our furnace would have been compliant in South Georgia. Same exact load. But what they're saying is that you don't have a lot of options in a warmer climate. You sometimes have to oversize your furnace, so they give you a little bit more a little bit more wiggle room. Here's what you want to think about. If you're putting in a furnace and you know good and well that furnace is way oversized, even though you meet within this in these bumpers here, you may want to think about installing the two-stage remodulating furnace. That way you'll run a lot in stage one. I installed a lot of furnaces in North Carolina, and I bet you most of them have never seen the call for W2. It just doesn't happen. You're not using them. So, but at least you're there compliant. So try to get in the habit of installing two-stage furnaces. I mean, we're seeing less and less single-stage furnaces as, energy efficiency and everything goes up. But if you have a choice, install a two-stage furnace. Everybody is just more comfortable, even in a cold climate, they're more comfortable with a two-stage furnace. All right. It talks about high altitudes also. And high altitudes above 25,000 feet, your furnace is derated. So you bought a 50,000 BTU furnace, but it's not putting anywhere close to that because in high altitudes, everything kind of changes. So what they're saying is that your minimum heating size needs to be 1.25. So if you're in a high altitude and you're putting in a furnace, knowing that furnace is derated, it's the second it comes out of the box. Let's say you have a load of 43,000 BTUs. The minimum size furnace that they want you to put in is 1.25. So you would need to have something with the output of at least 53,000. So would you put in a 50,000 BTU input furnace in this job? Would it keep up? No, because the 50,000 only puts out, if it's 96%, only puts out 48. We need to be at least 53. Now that's in a high altitude. All right. If we don't have anybody in high altitudes here, we can skip this slide because unless you're putting this thing on top of a mountain.
Please keep talking.
Okay, Brett. Yeah. So again, if you're above 2,500 feet, you take your load, you multiply it by 1.25, and that's the minimum output furnace that you need to be putting in. All right. That's on page 26 of Manual S.
Quick question.
Yeah.
Is the max still 1.4?
Manual S does not, that's the only guidance they give us
Okay.
that I'm aware of.
Okay.
So I would be as close to it as possible, because oversizing the furnace is just dumb. But, I don't think they gave us a max. But just knowing that the 1.4 or 2.0 is about as high as they want you to go anyway. So just get as close as to the 1.25 as you can. Now let's talk about air conditioning and heat pumps. We're in a hot mixed climate. So when we look at this climate map here, we're down in here where we get some heat, get some humidity. Winters aren't as bad maybe. So we got sizing limits for air conditioning and heat pump. Page 22 of Manual S. This time they give us 3 sizing factors that we need to stay in. We've got 3 sets of bumpers that we need to look at. Total cooling, we need to stay between 0.9 and 1.2. And notice that before we even go there, notice that this is the equipment that we're talking about. Single speed equipment when your cooling load is less than 24,000 BTUs. So we're talking about a small house, and we're trying to put in a single speed unit on a small house where our load is less than 24,000 BTUs. So this is the only case where this slide applies. All right. Your total cooling bumpers are 0.9 and 1.2. Sensible cooling, remember that's the sensible is what changes the temperature in the thermostat. All they want you to be is at least 0.9. All right. But they allow you to go down as low as 0.9. So you can be 90% of the sensible cooling load, and technically you're Manual S compliant. You can be slightly undersized. Let me get someone to unmute. Why do you think we're allowed to be slightly undersized on cooling?
To take out the humidity.
Sure. Yeah. Take out the humidity. Manual J has some. Go ahead. Someone else?
Is it because we can always be a little bit warmer, but making sure we're not too cold is more important.
Yeah, but they want you to be able to maintain the temperature. One of the other reasons is that Manual J tells you, like on page 4 or something, that there is fluff built into Manual J. So if you're 90% of the load, you're probably okay because there's fluff built in. You don't want to add fluff to overinflate your load in Manual J, but there's already fluff built in. Plus, if it is that hot during the day, it ain't going to stay that hot forever. The sun's going to go down in a couple hours and your house will start cooling down. So they allow you to be 0.9 of your sensible. Now, notice this. This is a really important one, and you're going to see this in all of our cooling calculations. They want you to be 1.0, at least 1.0 of our latent cooling. That's our moisture load. We have to meet our moisture load. We have to be 100% or higher of our latent load. And why is that? Somebody unmute. Why do they not allow you to be 0.9 of our latent load? They want you to be 1.0 or higher. Talking about moisture.
Is it to take all the humidity out of the house?
Yeah, because humidity is super important. So we're allowed to mess around a little bit with sensible cooling. We do not want to mess around with latent cooling. If your equipment does not meet 100% of your latent load, do not install it. Or do not install it that way. Maybe you can play around with airflows and get it there, but do not install it. That's at Manual S. They do not mess around with latent, and that's because of mold and health concerns and humidity and all that stuff, okay? Even though you have a dehumidifier from Santa Fe, a great dehumidifier, Manual S does not want you to, on a Manual J design day, they want your air conditioning unit to be able to handle that load. And Nikki will tell you the dehumidifier is not for your Manual J design day. The dehumidifier is for the 99% of the other times when it's not that temperature. We'll let Nikki get into that here during her side. So again, this just applies to total cooling load less than 24,000 BTUs. So let's do a quick sample load. We do our load calculation, small house, high efficiency house, whatever. We come up with a load of this. 23 total, 18 sensible, 5 latent. Pretty standard load. Okay. So we fall in this category. If we're trying to figure out where our guidance is, we would go to page 22 on Manual S because that's where we fall. So let's take our total load. And we're going to match it with, let's say we're going to go for a 2-ton piece of equipment. And surprisingly, this 2-ton unit actually puts out 24,000 BTUs. Normally they don't. All right. But let's just say that, it's just this magical piece of equipment where the manufacturer isn't trying to call it a 2-ton and it's actually a 2-ton unit. So here's our equipment capacity. Here's our load. So what we're doing is comparing these lines with each other. So our total load, and then when we set these bumpers up, our total cooling 0.9, we can be as down as 20.7, and we can be as high as 27.6. Our total capacity is going to fall in between these two bumpers. So far, we're good. Now let's see what happens with sensible load. Our sensible load, we can be, as long as we're higher than this bumper right here, we're good. Where is our sensible capacity? It's right here. So we're good. Now let's take a look at that latent. We need to be at least 1.0 over latent load. And are we? No. So are we installing this unit? Not yet. Maybe there's something we can do with this unit though. All right, but right now, this does not work. And I'm going to tell you, like when you're looking at equipment and you're trying to do Manual S the right way, I look at latent first, especially in a humid climate. This is the first number, because if it doesn't make this, it doesn't matter what these guys do. This is like your end all be all, your latent load. All right, so latent capacity is too low. We'll talk about some things maybe we can do about that here in a minute. Now, let's take a look at if our cooling load is more than 24,000, and we're talking about a single stage unit. Let's take another load. This time we're 25,000 BTUs, our total cooling load, 19 sensible, 5 latent. All right. Now we're going to be on this chart because our load's more than 24,000. So notice here that they want us to be between 0.9 and 1.15 of our total load. All right. So again, we have to do 0.9 times our load. And we come up with 22.5. All right. All we did is multiply 0.9 by our total load. We take 1.15 of our total load. We come up with this number, 28.7. We need to be in between these two numbers. This unit is too high. So things aren't looking good right now. Looks like we're a little oversized. But let's go ahead and go through the process. Let's do sensible latent and see what happens. 19 is our sensible load, where we need to be at least 0.9 of that. So that's 17.1. And what's our capacity? We're well above that. So actually, we're compliant on the sensible side, right? Now let's take a look at that latent. That's a really important one. We need to be able to meet our latent load. We have to at least get to this line right here. What's our latent capacity? All right, we're exactly there. So we have a situation where our unit is compliant with latent. That's really important. We're a little bit oversized on sensible, and we're too oversized on total. So would we use this unit is the question. Do you think there's anything we can do? Or do we have to go down to, like, instead of using a 2.5 ton, do we have to go down to a 2 ton?
Adjust
Should
the
we go
blower
down?
speed.
Go
Lower.
ahead, Perry. What was that?
Adjust the blower speed.
Yep.
You must know what my next slide is. All right, here's how we can fine tune. Now, your blower speed is not going to turn a 4 ton into a 2 ton. Okay. It's called fine tuning. All right. But less air means that our total and our sensible BTUs are going to go down, but our latent percentage is going to go up. If we move more air, we're moving more BTUs, but less of those BTUs are latent. So what we can do, if we reduce our airflow, this is what ends up happening. Did y'all catch that fancy little graphic that I just created there? It's pretty cool, right? Yeah, PowerPoint skills. All right. So when we reduce airflow, the total and sensible go down, and our latent goes up. All right. So could we? A lot of times we can get a unit to be compliant just by adjusting airflow and looking at the equipment specs with that airflow if they give it to us. All right. The other cool thing that Manual S tells us is that we can take 50% of our excess latent capacity and we can apply it towards sensible. So let's say that we had a unit where everything looked all right. We had plenty of latent, but we don't quite meet that 90% sensible. What Manual S is saying that is if you got a lot of latent, you can take half of that and you can give it to your sensible. And that may be just enough to get you within compliance. All right. It's because there is a little bit of sensible work that happens when latent work happens. And the drying effect that your latent capacity has actually helps your building feel better. So it's a little trick sometimes if you just got a unit that's got way too much latent capacity and you can't really get the other numbers up, you can apply a little bit of that latent to sensible. All right. All right, let's talk about two-speed equipment now. I'm a big fan of two-stage units. Here are your bumpers. If you recall, the single-speed equipment, they told you could only be 0.9 to 1.15. Two-stage equipment, you're allowed to be a little bit more oversized. And why do you think that is? Why do you think we're allowed to be 1.25 oversized instead of 1.15? If you got two-stage, why do you think they give you that little extra allowance for being oversized? Anybody?
Because most of the time you run at a lower capacity in a single stage.
Right. Yeah. Worst that can happen, it backs off in the first stage and it starts, going back and forth. So they still don't want you to be like egregiously oversized, but they give you a little more wiggle room. The other thing is, other than Rheem and Rudd, I'm not aware. Well, I think other brands are starting to do it, but there for a little while, for a long time, the only two-stage units that were available out there were in whole ton increments. You couldn't find a 2.5 or a 3 ton in a two-stage. Now you can start doing that. Riemann Rudd's offering. I know some of the side discharge inverter units are starting to offer it. But years ago, if you want a two-stage unit, you had to choose between 2-ton and 3-ton. So they gave you a little bit more allowance because they knew the equipment, the equipment choices weren't there. So let's do a sample problem. Here's our load, and here's our equipment. We got 25,000 total, 19 sensible, 5 latent. We're like, okay, well, we're probably going to start with the 2.5 ton. Are we going to be compliant? All right. Well, here's the, excuse me, guys. Someone's blowing up my phone here. All right. Here's our bumpers. Sizing limit, of course, is the sizing factor times the load. Our 90% of our total load is 22.5. And then our upper bumper is 31.2. Our unit at 30 falls in between these two lines. So we're good, right? Our sensible, we need to be at least 90% sensible. And we're well above that. So we're good so far, right? And then it looks like we meet our latent exactly. So is this two-stage unit manual less compliant? Can we go ahead and install this equipment at its current state? Did it comply in all 3 categories? Nod yes, nod no. What do you think? Yeah. Yeah, we can put this unit in. We're in between the bumpers here. We're above this bumper, and we're meeting this bumper. All we got to do is meet it. Okay? Very good. Now let's start talking about heat pumps in heating mode. Hot mixed climate. So we're talking about putting a heat pump down here in the South. Lower Midwest. All right? Winters aren't that bad. You know, you do get a winter, but it's not that bad. All right. So this is what it would look like. You're going to try to match your equipment to your cooling load as best you can. If it's a really hot climate, like if it's in Florida somewhere, your heating capacity is probably going to be way over your heating load. John, if you can jot your question down and we're going to take a break here in a little bit and I'll answer it during the break if possible. I do want to get to it. All right. So a lot of times in the South, you end up having your heat pump can put out way more heat than you actually need it to. And that's okay. Because the worst thing that can happen is it shuts off. What we want to do though is we got to make sure that we're meeting this latent load and that we're properly sized for sensible. All right. So if your heat pump heating capacity exceeds the load, that's okay. And actually, you don't need to put any supplemental heat. Now, there's a difference between supplemental heat and emergency heat. Even though in a lot of units it's the same heat strip, there is a difference in the terminology. Supplemental heat is the heat that we need to supplement the heat pump so that we can meet our heating load. In this case, our heat pump's got it covered. Emergency heat is where it's in place of the heat pump. So there's a difference. And we've got a couple slides coming because of that. But a lot of times if you're in the deep South, especially a good heat pump, your heating capacity is going to be way over your heating load. And that's okay because you sized it for cooling. You're allowed to do that. Sometimes though, if you're more of in a moderate climate, maybe you're in Tennessee somewhere, they get cold winters. They had snow this week. Sometimes your heat pump may not be able to meet your heating load. We see that a lot. All right. Unless you're in the deep, dirty South, your heat pump's probably not going to meet your heating load. All right. What do? Do you put in the next size up heat pump and then you're all oversized on the cooling side? No, we're not supposed to be doing that. So in that case, it's appropriate for us to put supplemental heat in. All right. So, and then you would size the supplemental heat. We got a slide for that. And you also may want to think about emergency heat in case the heat pump goes out. All right. So in the mixed climate and a warm climate, you can have either scenario depending on the climate and the kind of heat pump you're putting in. But it is okay to use supplemental heat. You don't have to use supplemental heat unless you need it. You definitely want to think about emergency heat though. But again, that is optional also. Now let's talk about heat pumps in cold climates. Do we have a lot of people in cold climates here? Yeah. And so there is a huge push towards installing heat pumps, electrification, and there's a place for that. I don't think there's anything wrong with putting in a heat pump in a cold climate as long as you've done manual S. I also don't get personally offended when I see somebody burning a fossil fuel either. So I'm sort of in the middle there. But if you want a heat pump and you want the option to be able to power stuff off of solar, yeah, that's fine. That's heat pumps are great. I've been working on heat pumps my whole career. So let's talk about sizing a heat pump in heating mode for a cold climate. So let's say that you're trying to use a single stage heat pump for a cold climate. Let's say that you size it for your cooling because you want to meet that latent capacity and you want to be able to cool the house properly. Your heating load in a cold climate is going to be way higher than your cooling load. You see the difference in the height of this bar and the height of this bar. This is your reality in a cold climate, right? You got a really high heating load, not so much of a cooling load, right? So if you were to put in a regular 14 SEER single stage heat pump and you size it for cooling, this is kind of what you're looking like in heating. You're going to need a lot of supplemental heat for that customer to be comfortable. What problem do you see with this setup right here?
Heat strips are expensive.
Yes.
Electrical cost.
Yeah. Yeah. Once your customer gets their first heating bill, they're going to be coming after you. This is not a good idea. All right. Because of you're sizing it for here, but this is kind of how it looks like in heating mode. So that's with a regular single stage 14 SEER. We're not talking about a cold climate heat pump. We're just talking about the kind of heat pumps they put in homes down here in the South because we can get away with it. I don't recommend this for a cold climate. Heating capacity is way too low. You're going to have high utility bills. So don't do this in a cold climate. Don't go get a great deal on a 14 SEER heat pump and then just throw in a bunch of supplemental heat and say, all right, they're going to be coming after you. So I don't recommend, we're just going to make sort of one of Tim's rules. It's like, don't put in a single stage heat pump in a cold climate. Because like a single stage heat pump only goes up to about 14, 15, 16 SEER maybe. And the HSPF is somewhere in the low eights. That is not enough to heat a home when it's 0 degrees outside. All right. So don't do this. These are Southern heat pumps and they kind of suck in the South too. All right. Now let's go with a 2-stage heat pump. And what Manual S did, and they needed to do it, they just made it really, really complicated, is that they have standard sizing for heat pumps where you pretty much size for cooling. And like everything we've talked about so far about heat pumps has been standard. And then they said, okay, well, we need to create something for cold climates. So we're going to come up with advanced sizing for heat pumps. And they made like 50 options, it feels like. It's not 50, it's probably 7 options for how to size a heat pump in cold climates. And they took something and made it really, really complicated. I don't know how they could have simplified it. It was like an impossible task, but unfortunately, like we have all these different choices when it comes to advanced sizing of a heat pump. I'm going to try to simplify it. I'm going to leave a few things out because I don't think they're relevant a lot. But let's say that we get a 2-stage heat pump. We're like, all right, well, 2-stage is better than single stage. All right. We're going to use this advanced sizing. And what we're going to do is we're going to size this heat pump more for a heating load, knowing good and well that it's going to be oversized and cooling. But hey, it's a 2-stage unit. So we're kind of banking on it never really going into second stage and cooling. And so Manual S gives you some guidance for making those decisions. So again, like we're going to size this heat pump for maybe almost all of our heating load. Maybe there's a little bit of strip heat in there, knowing that we're sizing it for heating and that it's probably going to run in first stage during the summer. How high can you go? How oversized can you go with a heat pump? Well, here's what they're telling us. The maximum heating size factor shall not exceed 1.2. So what they're saying is that you take your heating load and your heating capacity cannot exceed 1.2 of that. They're telling you do not so grossly oversize this heat pump that it's going to absolutely suck in cooling. All right, so they're giving you an upper limit here in heating. Do not exceed 1.2, and the minimum cooling capacity factor should not exceed 0.8. So what they're saying is that when this unit turns itself down, it cannot be 80% of the cooling load. It can't be higher than that. So that's really hard, and I get it. Like, this is really hard to understand. So I'm trying to make a visual of it. What they're saying is that your heating side, you can't go above 1.2. And when your unit goes down to its first stage, its lowest speed, you need to be below 0.8, or else it's still oversized. Now, this unit, when it goes down into first stage, it's still well above this 0.8 mark. So that means that we're actually, this heat pump's not going to work. For us to be able to size it enough for heating means that we're going to be oversized in cooling beyond those bumpers that Manual S gave us. So here's going to be another rule, because I've looked at a lot of equipment specs and I've not yet found a two-stage heat pump that meets Manual S in a cold climate. All right. We need to be able to use dehumidification. So let's say that you're like, okay, fine. I am going to pick a heat pump that will, when it turns down to its first stage cooling, we meet that 80%. But unfortunately, this is all it'll do in heating, which means that I have to do the rest in supplemental heat. And that's a lot of supplemental heat. I know I'm not throwing numbers here, but like, that's a lot of supplemental heat. And this is kind of how the numbers work out. And so what I'm telling you is that typically a two-stage heat pump, because they're not cold climate heat pumps, a two-stage 16, 17 SEER heat pump is not designed to run and really produce heat at 0 or single digits. All right. And that's unfortunately the winters that you get in cold climates. So if you size your heat pump too aggressively so that you can still meet the cooling side of Manual S, it's going to suck in the winter. If you size it for winter, it's going to suck in summer. And that's how a lot of two-stage heat pumps, I'm going to say they rarely work. Maybe you can find one that works. Sometimes these two-stage inverter heat pumps might get you there. Depends on your load. Depends on, how cold is your winter, how humid is your summer, that sort of thing. I can't paint, this thing with a broad brush, but just be really careful. Even two-stage heat pumps rarely really work in a really cold climate. Like, we're talking about like, upper Michigan flannel wearing states. Like, the two-stage heat pump rarely works. Now we get into variable speed heat pumps, cold climates. Again, they're saying that when it turns itself down, it cannot be more than 80% of the load. And so you're looking for a heat pump that it can turn itself down. Again, variable speed, they can turn themselves down, but there's still limits in how low a variable speed compressor can go. All right. It needs to be able to turn itself down not to exceed 0.8. But then here's the kicker. When it does turn itself down, you still have to meet the latent load, because ACCA is really concerned about meeting the latent load. We've got to be 1.0 over latent load. And so you end up, this is what you need out of your inverter unit, but you still got to be able to meet the heating load. So you're asking this thing to do almost the impossible. All right. Not only does it need to meet the heating load, but when it turns itself down to meet the cooling load, it still has to meet the latent load. And that's hard for a unit to do. All right. And what we're getting at is that when you use heat pumps in cold climates, supplemental dehumidification is your reality. All right. Especially in a super cold climate. If you've got even a month of humid weather, the only way we can make heat pumps work is to throw in supplemental dehumidification. Maybe you're in a weird climate where you can get away with it, but most climates, we cannot get a unit that's okay here that can also turn itself down and still meet the latent load. All right. And the problem is also that their Manual S is stipulating the minimum latent capacity shall not exceed 1.0. What they're saying is when this unit turns itself down, when you look at the specs of that unit, the latent capacity needs to be equal to the latent load. The problem is nobody publishes that data. Everybody publishes what their latent load is at your design temperature. They'll publish how far this heat pump will turn down. They'll publish what your total BTUs is at its minimum capacity, but they don't break that total down into sensible versus latent. So Manual S created a rule that nobody is allowing you to be compliant with. So you have to assume that your inverter unit is not going to do any latent work. So that's why you need the dehumidifier. So supplemental dehumidification is going to be your reality if you're working with heat pumps in cold climates. We're up on our first break. Let's take 5 minutes. We'll come back at 7 p.m. If you have any questions, now's the time.
Yeah, I was going to ask if you could explain what parts of the equipment actually, like what variables that the equipment does actually changes the sensible, the latent, and the total
Yeah.
load.
Essentially, it's compressor speed. So if you have a variable or multi-stage compressor, that changes the capacity, and it is airflow. So we can change the ratio of sensible and latent by changing airflow. And then your compressor is also going to speed up or slow down. That's going to change these as well. Those are the only two adjustments you can make. No
Okay.
residential.
Sweet.
I've got a question in the chat. When you're stating equipment capacity, are you factoring the adjusted performance data, or are you based on ACA manufacturer rated? We're talking about adjusted performance data. We're going to get into that next. We've been talking about like what's the capacity of the unit, but I haven't yet shown you how to actually find that. We're not talking about the AHRI rating. We're going to talk about the performance data from the equipment, and that's what we're going to get into next. But I just sort of had to start with these fundamentals. So, our total capacity, sensible capacity, latent capacity, where do we find that information? I'm going to show you how here in the next slides.
Tim, you know what resonates with me when we're going over selecting equipment? A lot has to do with the load calculation itself. Back in my early years, I did load calculations, and I put factors in there and added percentages and things of that nature that I shouldn't have been doing. Now that I've learned better, we're doing the load calculations and we're being more aggressive.
Yeah.
But at the end of the day, all we're doing is we're handling the load for 1 hour at peak. And like you said, there's a lot of extras in there because, say for instance, if you have a ceiling fan, for instance, it may be on and it may not be. But we factor in the ceiling fan when we do the load calculation. Another thing too in Manual J, it says it from time to time, designer's discretion. There's some things that's not, just etched in stone.
Yeah.
Yep. At the end of the day, we put all these numbers together, then we start looking to pick out equipment. If we didn't do the loads correctly, and we oversized the load, then we're going to oversize the equipment,
Exactly. Yeah. So like one of the softwares out there, CoolCalc, a lot of its defaults, its standard defaults, they're putting like people and appliances in every room. Now it's up to you as the user of CoolCalc to change that. But if you don't know to do that, then that's going to overinflate your load. At the end of the day, like doing a load calculation is a scientific, wild, assumptive guess. It's a swag. We're trying to avoid it just being a wag. We're trying to make it at least scientific. But at the end of the day, I tell people it's shooting balloons with shotguns, not bottle caps with rifles. All right. Just do your best to put in the right inputs, be aggressive. but that number is not going to be, if you have 10 smart people looking at the same job, all their load calculations are going to be different.
Yeah.
And all of them are probably right because all of them are going to be within probably half a ton of each other.
Yeah.
Hey, Tim, could I ask a quick question?
Yeah.
So when we talk about, and I've heard this and known this, that, half of our latent capacity becomes sensible capacity, how much do we take that into account with sizing? Because like where I'm at, the last house I did had negative 337 BTUs of latent capacity. And so it's like, do I take that into equation when selecting my equipment size, which is going to make my heat pump even smaller in a cold climate, which is really going to even make the supplemental heat run more? Or is that just kind of like free capacity that you don't account for and it does its job when it needs to?
I mean, if you're in a place with negative latent capacity, you're going to be in a cold climate. So you would size it for heating and you would try to meet, I mean, there is a manual S advanced sizing instructions for that. It's not one of the ones I went over because it's so rare, but they do tell you that, you size for heating. You don't want it to be so oversized in cooling. And then obviously you don't have any latent heat to worry about. So that is in manual S. Can try to find exactly what it is. It's just such a rare, there's only a couple of climates that actually that is the case. And I just didn't cover it in this class. But you don't have to worry about the latent at all. So you're gonna size for heating and
Gotcha.
try to size aggressively for heating. Don't oversize it for sure because you're not going to need hardly any of that for cooling. For example, manual J a lot of times overinflates your heating load in the winter. So I tell people, if you're sizing it for heating, maybe go 90% of the heating load. If you're really trying to, if your cooling load is also a factor and you're trying not to oversize it for cooling, go 90% of your heating load. Throw 5 kW strip heat just in case. But most likely, manual J has overinflated your heating load. I mean, there are some cases when it doubles the heating load on a building, especially a slab home, because it has to make assumptions that may or may not be the case. And your heating load is very rarely what your heating load actually is.
Gotcha. Thank you.
And you can find that out like on a typical, design day at 5 degrees outside. If you got a furnace in there or you can time the furnace. More or less how many BTUs is putting out of output based on the model number of the unit and assuming it's running correctly, you can time it. How long's the heating cycle? And you can do a little bit of math and you're like, okay, well, I'm putting out 50,000 BTUs and it ran 45 minutes out of an hour. So my actual heating load must be 75% of 50, and you're going to be pretty close. Now, your manual J probably said you had 90,000 BTUs of heating load. That's the reality of it. So very rarely do you need to worry about like, okay, if I've got to hit the world's going to end if I don't get 100% of my heating load. And I know that contradicts what I just said, but manual S is going to tell you one thing, and then reality is kind of a different thing. But we'll get into Tim's simple rules for sizing units here in a little bit, and you'll see that advice come out. Let's get into supplemental heat, though. Supplemental heat is usually electric strip heat on a heat pump, and it's covering what the heat pump can't cover on a design heating day. So let's say this is your heating load in the winter. It's 45,000 BTUs. And when you look at the specs of your heat pump at whatever outdoor temperature this is, we're not saying what it is because it's not relevant. Let's say that your heat pump only puts out 30,000 BTUs. Well, that means that you've got 15 that are unaccounted for that you need to have supplemental heat for. All right. And so what are the guidelines? How big strip heat are you allowed to put in? Can you oversize your strips? Well, they tell you that you're allowed on your supplemental heat to be 90.95 to 1.75 of the supplemental heating load, not the total load. Here's what that looks like. Here's your supplemental heating load. If we look at what our heat pump can do, our supplemental heating load starts here. Doesn't start down here because our heat pump's got us covered up to here. Okay? And what they're saying is that when you size your supplemental heater, we need to be in between the 0.95 bumper and the 1.75 bumper. All right, but that would start at 30,000 BTUs. That's where your zero is because your heat pump's covering you up to this point. So here are the bumpers on supplemental heat. So then, okay, we've got what's the question is still what is our strip heat size? You know, what are we quoting in the job? Well, this is a nice picture to take. It's a quick sort of a quick reference for strip heat. 1 kW is 3.4 MBH. All right. And then as we get into the common kW sizes, you see how many BTUs they actually equal. So what size strip heat would we put in here in this case? Well, we need to be in between these two numbers. A 5 kW would work because it puts out 17,000 BTUs. And a 7.5 would work. Both of them are compliant. All right, so our heat pump got us part of the way there. And then our strip heat needs to get us the rest of the way there. But we're given a pretty wide range in between these two bumpers. And so, again, what you're doing is you're taking your supplemental heating load, which is whatever's left that your heat pump can't cover. You're multiplying that by 0.95 and you're multiplying that by 1.75, and you're finding a strip heat that's somewhere in between. In this case, you have two sizes that would work. Both of them are compliant. All right. Manual S also says that if you have a variable speed equipment that meets 100% of the heating load, you're not required to have supplemental or emergency heat. There's a lot of Mitsubishi Hyperheat systems that I designed for homes that don't have any strip heat in them because they more than cover the heating load. And, you know, it's a passive house or a house where they don't like strip heat because it's not efficient enough. We just don't put it in there. Now, heaven help them if their heat pump goes down in the middle of February. But that's, you know, we're not required to put in supplemental or emergency heat if your heat pump can handle the load. You may still want to. But you sort of get some of these clients that are like really green minded and, you know, anything that's just, you know, strip heat or, you know, heaven help you if you're, you know, setting something on fire in the house, you know, they panic. And so like, no, we don't want any of that in there. Okay, well, Manual S says you don't have to put one in there. You might be an idiot if you don't, but, you know, you're not required to put one in. I know some places like in Canada, they make them put in emergency heat because like if your heat goes out, like you just die. So I know some places in Canada, they will make you put in like, you know, 20 kW strip heat on a heat pump as a backup. And it may never run. And then the one time it does run, I don't even want to know what it smells like when that thing finally burns off after 17 years of not running, but we won't go there. All right. Emergency heat. Emergency heat there is there to take the place of your heat pump if your heat pump stops working. It's not supplemental heat. It's not there to run along with your heat pump. It's there to run instead of your heat pump. So in that case, we need to carry more of the heating load with the emergency heat. Here's Manual S. They say you can size your emergency heat anywhere between 0.8 and 1.78 of the heating load, which in this case is 45 MBH. So in this case, where are our bumpers? Well, we take our heating load, 0.8's down here, 1.75 is up there. Either one of these, the 7.5 or the 5 kW that worked for supplemental heat, we actually need more because now they've got to carry what the heat pump could do also. So a 10 kW gets you here, and then 15 kW gets you actually in between the bumpers. So your emergency heat actually needs to be 15 kW. So let's think about this. We're pricing a job. and we want to put in emergency heat. We're going to need to put in 15 kW for emergency heat. So when we go into supplemental heat mode, do we want all 15 kW coming out at the same time? No, we're going to separate those heat strips for supplemental heat. Supplemental heat, that 15 kW is probably a 10 and a 5 or maybe 3 5s. We want to stage those out, is what we're saying. We want to stage, because if all 15 kW comes on top of your heat pump, that is scalding hot air coming out of the vents, and you don't need it. All right. So what I'm getting at is when you start getting into the 10 kW plus heat strips, don't just take all those white wires and grab a big fat wire nut and just wire them all together. Stage them out with the thermostat. That's what you want to do. All right, dual fuel. I love dual fuel heat pumps. Best of both worlds. Manual S makes it really easy for us. They say, all right, when you're dealing with the dual fuel, whatever we told you to do for furnaces, do that. Whatever we told you for heat pumps, do that. All right. So when you have dual fuel, it's actually a good idea to size your heat pump for the cooling load. All right. Now we can aggressively size it. We're going to be closer to our latent capacity. Like everything starts working pretty good. And we know that the heat pump, if our heating load is here, we know that our heat pump's not going to get us there on the heating side. We know that the furnace is going to have to kick in at some point. All right. We're allowed to, we just essentially, in a cold climate, you may be able to use a single stage 14 SEER heat pump because you're not asking it to heat the home, not down below like 40 degrees. So you can actually throw in some of these cheaper heat pumps in there because you've got dual fuel. But you would definitely want to size the furnace for the heating load. Size the heat pump for the cooling load and know that at some point the heat pump's going to give out and the furnace is going to have to take over. And that's okay because come summertime, that heat pump is sized really good for cooling. And that's important. So you can't really talk about dual fuel and heat pumps without talking about balance points. And man, we can overcomplicate balance points, but we don't have to. There was calculations. I remember when I was going to school and we spent like 2 weeks on calculating a balance point. Do not spend a lot of time trying to figure out whether your unit is going to need supplemental or dual fuel heat at 35 degrees or 33 degrees. It is not that important. All right. What are we in the business of doing? We're in the business of keeping people comfortable, right? We also don't want them to have to sell a kidney to pay for their utility bill, right? So there's a pretty big window in between those two extremes. So here's what the heat pump balance point is. We know that the heat that a heat pump puts out when it's really warm outside, when our outdoor temperature is really hot, a heat pump puts out a lot of heat. When it's 50 degrees outside, every heat pump works great. All right? Because it's only 50 degrees outside. The house doesn't need a lot of heat, and the heat pump has a lot of heat to give. But as we start getting colder outside, the heating requirement for the house goes up, but the heat output of the heat pump goes down. So at some point, these two lines cross. Once we're on the right side of this line, now we need supplemental heat because the heating requirements of the house exceed the heating capacity of the heat pump. So now the heat pump needs a little bit of help. Now, whether that outdoor temperature is 26 degrees or 35 degrees, you can spend a lot of time trying to calculate it and you still might be wrong. Thank you, Nikki. I saw that. We'll be ready for you at 8. You can spend a long time trying to figure out what that balance point is, or just get a smart thermostat that figures it out for you. A learning thermostat. All right. And you can put in a lockout, or you can tell the thermostat, hey, when you start seeing the heat or the temperature in the room stop going up with a heat pump, kick in emergency or kick in supplemental heat. Like you can tell this Ecobee thermostat, even a Nest, even that dumb hockey puck of a Nest thermostat, you can tell it when At Honeywell, same thing. They call it droop. When you start seeing the temperature of the room, we're trying to heat the house, and all of a sudden it flatlines because the heat pump is not keeping up. When you see that happening, kick in supplemental heat. All right. And you can put in lockouts. You can say, hey, I do not want supplemental heat to run above 40 degrees because it should never have to. You can put those lockouts in there. Sometimes code requires you to do that. I don't know if any inspectors are smart enough to check back after you, but you can. But these thermostats, when you talk about droop and some of the other, every thermostat calls it something different. What you want to look for in those configurations is, when to kick in supplemental heat. One, I think Nest calls it's economy and comfort. Economy is they're not going to cut in those heat strips for a while. You're just going to have to get cold. And then comfort is they're going to be very aggressive in cutting those heat strips on. They're not going to give the heat pump a chance to keep up. So there are different thermostats call it different things. I would not spend a lot of time trying to calculate balance point. You will start to figure out what the balance point is for a certain house in your climate. Just if you install these thermostats, you start looking at what your house does, what some of your clients' house does. When I install an Ecobee thermostat, I ask them to include me in their family, so to speak, in their Ecobee account. And on a really cold day, I'm a nerd. I don't have anything else to do. So I go and I start looking at people's thermostats and I'm like, oh yeah, this house right here is a newer house. It's 26 degrees outside and it still doesn't need strip heat. This is an older house. Looks like we're starting to need strip heat and it's only 37 degrees outside. And I start learning patterns. So that's what I'm saying. Like if you have a way of gathering data, putting in Ecobees and looking at that data, use that to your advantage and you'll start seeing patterns. Harold, I see your hand on our next break. If I could answer your question then, I'd appreciate it. But please write that question down. I want to get to it. All right, here's the slide that everybody needs to, and wait till I get through the whole thing before you take a picture of it. All right. We've talked about a lot of things, right? Talk about sizing furnaces, sizing air conditioners, whether if you have a single stage unit, a two-stage, a variable speed, if you're in a hot climate, a cold climate. We've talked about a lot of rules, and trust me, like Manual S has got a lot more rules we haven't even considered. But in the end, we're in the business of making people comfortable, and we prefer for them not to have to sell a kidney or their firstborn to pay for their utility bill. We're just trying to stay in between those two bumpers, right? So here's what it boils down to. If you're in a warm or mixed climate, the South, the Midwest, the Mid-Atlantic, latent cooling, one of the most important things. Have enough. When you look at your unit specs, make sure that you have enough latent cooling. And you're probably still going to need to offer dehumidification because we get some swamp butt weather here. And a lot of times, even a unit, when it's sized for latent cooling, there are some weather patterns that's still not enough. So offer dehumidification. But that's the first thing you look at is whether or not you meet your latent load. Sensible cooling. Don't just arbitrarily have more than what you need. You can be slightly under. Remember, we said we can be 0.9 of our latent or of our sensible load. All right. So be within 1,000 BTUs of your sensible. You'll be fine. If you do those two things, your total cooling will take care of itself. All right. Play around with airflow. Make sure you're meeting your latent load. Make sure you're not grossly oversizing your sensible, but you're pretty close to your sensible. Total cooling is just latent plus sensible. You take care of latent, you take care of sensible, you've taken care of total. All right. So that takes care of itself. Gas heat, have enough. And also assume that Manual J is probably overinflating, is being a little bit dramatic about how much heat you actually need. All right. It's especially on a slab house. Heat pump heat. Again, we're talking about warm mixed climate. Size your heat pump for cooling. All right. We know that the heat pump may not keep up on a cold winter night, but guess what? We only get like 5 of them. And if we do get a cold spell, people are usually okay with their electric bill being slightly higher that month, as long as it's not all winter long. But let's face it, what are our winters like in the South? They're kind of a joke now. All right. So size your heat pump for cooling. Put in supplemental heat for the rest if you need it. Only if you need it. Supplemental heat. You add it to the heat pump and only what's needed. Don't put 15 kW if you don't need 15 kW. You don't want the lights dimming every time the supplemental heat comes on. Emergency heat. Stage it if possible. Don't just take all your strip heat wires and wire them together and, when the thing comes on, the lights dim. Don't do that. Stage it as more comfortable for your occupant too. All right. And it's the other thing that we didn't really talk about. It's your emergency heat. Manual S tells you you only have to meet 80% of your load. Think about it. It's an emergency. We're just trying to keep grandma from freezing to death. That's all we're trying to do with emergency heat. We're not trying to keep it a balmy 70 degrees. We're just trying to keep the pipes from freezing and hopefully grandma doesn't die in her sleep. All right. If we can keep the house 62 degrees, grandma can put on a blanket and she'll get through the night till we get our heat pump running. And that's what they mean by 80% of the heating load. Because if we try to size emergency heat for 100% of the heating load, that's a lot of emergency heat. And we don't need that. Cold climates. Variable speed cold climate heat pump only. All right, so we're going to get into what is a cold climate heat pump in a future slide. All right, just because it has an inverter in it does not mean it's a cold climate heat pump. There are certain other criteria it has to meet. All right, so think about, if you guys know, like the Mitsubishi systems, there's the Mitsubishis and there's the Mitsubishi Hyperheat. There is a difference in what they do when it gets down to single digits between those two models. We'll talk about that in another slide. Dual fuel. Size your heat pump for cooling, size your furnace for heating. That's simple. Latent heat. Just know if you're sizing your heat pump for heating, you are not going to have enough latent capacity, the way that heat pumps turn down. All right, it's just not going to be enough. So just go ahead and know, just wrap your head around the fact that unless you're in like the climate of the one dude that said that he has a negative latent load, unless you're in Idaho or Boulder, Colorado, you're probably going to need some supplemental dehumidification. Heat pump sensible cooling. You are going to have too much sensible cooling if you size your heat pump for heating. It's just how it works. If you're in a cold climate and you size your heat pump for heating, you are going to be oversized for cooling. That is just how it is. So try to mitigate that. Offer a variable speed unit so that your unit turns itself down. Gas heat, again, have enough, because when it gets cold, it's going to be the only heat you got. Electric supplemental heat, only if needed. So, there's a lot of Hyperheat Mitsubishis that I design. It doesn't need supplemental heat. Those things are rock stars when it gets down to single digits. And we don't need it. So only if needed. Maybe you sprinkle 5 kW in there just in case if you think you're aggressively sizing for heating. That's fine. And then emergency heat, stage if possible, and only 80% of the heating load. We're not trying to maintain 70 in the house and the heat pump goes out. We're in emergency mode. We're just trying to keep everybody alive. All right. All right. So go ahead and take a picture of that. Give you a second to do that. This is the slide that ACCA hates because it's an oversimplification of a very thick book that they wrote. But, this covers the intent of Manual S. But some of the purists out there, and actually it was funny, last year when I taught this class, Wes Davis from ACCA signed up for this class and showed up without telling me. And I'm like, all right, Wes, this is the slide that's probably going to piss you off. But he was super cool about it. He offered some really good feedback at the end of the class. But yeah, we're just trying to simplify what we're doing here. We can't spend hours trying to size a unit. That's the reality of it. All right. This goes back to one of the comments that came in earlier. AHRI versus our ACCA design conditions. Everybody knows about the AHRI certificate, right? That's the matchup. We have to put in a system that has that matchup, or else it voids warranty, and apparently the earth stops spinning and all kinds of bad stuff happens. But the problem with now AHRI, if you look at that certificate, it's going to tell you what the cooling capacity and the heating capacity is. And you're like, all right, cool. I've got that. That's what I plug into those bumpers that Tim was talking about. No, you can't do that. Because the AHRI, when they're testing those units and rating those units, the conditions that they're rating it at is 80 degrees dry bulb, which is like pretty warm, and 67 degrees wet bulb, which is pretty balmy. And it's at 95-degree outdoor temperature. It's assuming you got 0.5 inches static pressure, which is an improvement from a few years ago when they only did like 0.1 inches static pressure. Like they just assumed we don't put ductwork on our units. And it's like the nominal 400 CFM per ton airflow. So it's a very like standardized set of conditions. That way they can compare every single unit's performance at those conditions against each other. And so that's where they give you the SEER rating and the HSPF and all those efficiency ratings at these conditions. The problem is when we put these units in the real world, we're not using these conditions. We're putting them in different sets of in different temperatures. The other thing that's not available is that they don't give you the breakdown between sensible and latent in your AHRI certificate. So how the heck would you know whether or not you're falling between those bumpers of sensible and latent if they're not providing that for you? It's not there for you to select the unit. It's there so you can compare whether or not this Carrier is better than this Goodman. All right. And it's not giving you its capacity at other outdoor conditions, at other indoor conditions, other airflows. It's just one set of conditions that we will probably never use in the field. So what you've got to do is go back to your manual J. And now you've got to look at the specs of the unit. They're going to have performance specs at the actual temperatures that you're going to run this unit at. So our indoor temperatures is going to be 75 dry bulb, 63 wet bulb. Well, now that's a lot different than 80 dry bulb and 67. There's a lot less heat in the air. So a 3-ton that was rated at 3-ton at AHRI conditions may only be able to pull out 2.5 tons worth of heat at these conditions. Your outdoor temperature is going to be all over the place. There's places where the outdoor temperature is 82 degrees in the summer. There's other places where it's 108 degrees in the summer. That's going to affect how many BTUs this unit puts out. Your airflow is going to change. We need to know what the sensible and latent capacity is at these conditions. We need to know what the heating capacity is at these conditions, not the 47 degrees that they tested at for AHRI. So these are the lab settings that are for your certificate, but you have to know what it's doing in the real world. And that means that you have to look up the unit specs. There are different ways you can do that depending on the unit. All right. So some manufacturers offer selection software, which makes it really easy. You put in a few inputs and it spits out to you what the unit's going to output. Other ones just give you a chart and you have to like look at the chart, and the chart has a bunch of numbers on it and it's really intimidating to look at. We're going to show you that it's really not that intimidating, but depending on what kind of unit it is, the selection of that unit and those performance specs is going to vary how they list it. So let's talk about ICP products: Carrier, Bryant, Payne, Heil, all those sister brands. Here's what you do. If you're a Carrier unit, just go to Google and type in my Carrier ratings. You're looking for this website right here. All right. Now this website, if you're a Bryant, you type in my Bryant ratings, my Payne ratings, my Heil ratings. You're going to see a website that looks similar to this. You're going to go on that website. Here's what it looks like for Carrier. You're going to click on this AHRI combinations ratings. Now, you've got a few things to put in. Let's say that you're selling the outdoor model line of this GH5 SAN5. You're going to need to start with a tonnage. Let's say we start with 24,000 BTUs. Pick your indoor unit that you think you're going to want to sell to them. All right. If you're a furnace, there's a place to put that here. If you don't know what these are or what choices you have, you can put in some minimum SEERs and HSPF and they'll give you a really long list of choices. But that list is really, really long. I like to put in as much information as I possibly can so that I only get 1 or 2 choices down here that I have to select from. So if you're a Carrier dealer, you know your model numbers, you know what your 14 SEER model line is, your 15, your 17 SEER. You're going to put in as much information as you can, and it's going to give you the list of units that kind of fall under those specs. So what we're going to do is we're going to hit this performance calc. And that brings us up to this screen here. Now, let's say that your sizing unit for my climate, Wilmington, North Carolina, outdoor design temperature, my manual J outdoor design temperature is 90. My winter is 28. And it hardly ever gets 28, trust me. When I did my load calculation, here's what my load count. This is my manual J results right here. So now I have to find a unit that falls in between those bumpers. So I'm going to pick an airflow. So for example, this is a 2-ton unit, that 24. So I'm going to pick an airflow that's allowable, and I'm going to see whether or not the unit is going to have enough capacity and it's going to fall within those bumpers. So this is a single stage unit. My load is higher than 24,000. And so I have to use these sets of rules right here. All right. So my sizing limits, you see we've gone over this already. Total cooling needs to be between 0.9 and 1.15. Sensible needs to be at least 0.9. And I need to be at least 1.0 my latent. I have to meet my latent load. So the question is this unit going to work? Well, again, I told you the very first thing you want to look at, especially if you're in a climate that gets any kind of humidity, start with your latent. And immediately right now we see that my latent capacity does not meet my latent load. So it does not matter if anything else on this unit is manual S compliant. It doesn't meet the latent load. It's not going to work. Now, does that mean that I just throw away this idea of using this 2-ton unit? Are there adjustments that I can make to maybe get it better? What are some of the adjustments we talked about to change that latent and sensible ratio? What's the main adjustment that we can do to fine tune it?
Fan speed.
Fan speed. So we can play with the fan speed right here, right? Play with the airflow. So right now it's undersized. And if you notice, like even our total and our sensible capacities are way low than the load. When we compare all these numbers, everything's undersized. All right. So is there anything we can do with the fan speed? Well, if we change this number, let's see what happens. All right. Now let's change same unit. We change the fan speed to 850 CFM. 2-ton unit. Now we're moving 425 CFMs per ton. All right. So we're moving some air through this. Now, what happened to our latent capacity? It got even worse. All right. Our sensible did go up. Our total went up. There's just no way this 2-ton unit's going to work. Like no matter what we do with our fan speed, you can play around with this all you want. It's not going to work. All right. So now let's go up to the next size up. We thought we were going to sell them a 2-ton unit because, we were close to 25.5. We're going to sell them the 2.5-ton unit now. You think it's probably a good idea to do this process before you give them the quote? All right. So now we're going to go with the 2.5-ton. We're going to start with 800 CFM. Not sure if that's going to be enough. All right. We changed our equipment, 2.5-ton. We're going to start with 800 CFM. Let's start with our latent capacity. Do we meet our latent capacity? Yes. So far, so good. We're slightly under our sensible, but remember I told you Tim's simple rules for sizing equipment? Like as long as you're within 1,000, like don't worry about it. So we're slightly undersized, but we're close enough on our sensible. If you take care of your latent, you take care of your sensible, your total is going to take care of itself. All right. So now this unit's looking a lot better, right? We still got to think about heating load though. Right size for cooling. Our heating capacity we know is well under our heating load, so we know we're going to have to use some strip heat, right? I don't know whether I actually go that far in the slide. No. All right, so that's kind of what you would do for a carrier system. All right, now let's talk about Mitsubishi Diamond System Builder. That's a program you would download onto your laptop. It gets updated periodically, and here's what that looks like. Let's take a job in Cincinnati, Ohio. Colder climate, right? But you know what? Their summer temperature is actually just as hot as it is in Wilmington, 91 degrees. All right. Cold climates get hot summers. They just don't last that long. But the winter is all the way down at 14. Here's what our load calculation looks like right here. Here's our results for our manual J, the sample problem. All right. So here's what Diamond System Builder looks like. If you're selling Mitsubishi, you need to be using Diamond System Builder. All right, we're going to pick, because we've got a heating load close to 24,000 BTUs. We're going to start with this 24,000 BTU unit, and this is not a hyperheat model. All right, I'm just going to show you what happens if we don't use a hyperheat model in a cold climate. So let's say, and these are old model numbers, these are 410A units, because I haven't had time to update all the new model numbers. They haven't published a lot of the stuff out. Diamond System Builder is a little bit behind on that. So I'm just using, like, if you recognize these as old model numbers, it's the intent that counts, okay? We're going to go in there into a window, and we're going to put in all of our design conditions. Same conditions that you see here. We're going to make sure that we put them in here. And then we're going to put in the unit, all the piping bends and the lengths and all that stuff that can derate a unit. And then here's what it spits back out at us. This matchup right here. Again, this is not a hyperheat model. All right, here's what it can do. This is our total BTUs. Here is our sensible. We have to subtract one from the other to get our latent, because I don't know why. I don't know why they just can't give us our latent, but they don't. So we're comparing our capacity versus our load. If you look here, we're meeting everything just fine. Even when you get your latent capacity by subtracting sensible from total, that's like 5,000 BTUs. That's way over our latent. Like in the cooling side, this unit's going to work just fine. All right, it's inverter. But notice what happens on our heating side. When we get down to that 14 degrees outside, this unit only puts out 14.3 because it's a non-hyperheat model. All right, it's an inverter, but inverter does not mean cold climate. All right, inverter does not mean cold climate. So notice that we've got a shortfall of almost 9,000 BTUs. All right, it's going to run a lot of strip heat if we put in this unit. Customer's not going to be happy. So now let's look at the same model line of unit, but instead we've got a hyperheat model. That's what that HZ stands for. Our cooling specs are really, really close. But our heating, it's a huge difference between these two units. That's what a cold climate heat pump does when it gets cold outside. That heating does not drop off until we get to the negatives. All right, that's the difference between cold climate heat pumps and not cold climate heat pumps. So you got to know, if you're in a cold climate, or if you're going to be putting a unit in a house and supplemental or backup heat's not an option, cold climate heat pump. All right, that's the difference between us putting 10K or not in a house. Trane American Standard, their selection tool, you got to be a dealer, or you got to really suck up to a distributor to get this, but or you just got to know a person. Somehow I was able to get both. I don't even remember. I don't want to remember what I had to do to get it now. So we've got when you go on their website, and you log in. Here's where you go. All right, and this is what's going to pop up next. You're going to do electronic performance data. This is the selection tool. Now, here's where you start off putting in all your design temperatures here. And then you're going to kind of put what your tonnage range is and what model outdoor unit you want to start off with. Again, these are 410A numbers. Just bear with me. It's going to give you a list of things of units that are going to meet that criteria. You're going to start off with the model numbers that you know that you're probably going to sell. This is the model that you guys use, whichever one it is. You're going to select this one. You're going to hit that report button. Brings up this screen. We're doing a job in Wilmington. Here's our design conditions. All right. So it gives you a chart. A lot of numbers on this chart. It may be easy for your eyes just to glaze over and say, you know what? I don't want to read this thing, man. I don't even want to do this. These charts are not that bad. There's a lot you can eliminate from these charts. The one thing is we're in 90-degree summer temperature. So immediately this part of the chart is not valid for us. We don't even have to look at it. Take a giant Sharpie if you need to and mark through it. We don't need it. We've just cut this chart in half. Our indoor design temperature, 75-degree dry bulb. That's going to be these numbers right here. These are different indoor temperatures. We're only going to be looking at the 75 column. So now all those can get marked out. We've just narrowed this chart down to just a few lines. Then our wet bulb. That's these rows right here, indoor wet bulb. We're only dealing with 63 because that's our manual J condition, 63 wet bulb. That's the wet bulb you're going to use every time in manual J. So all these, the 59, the 67, we don't need to worry about. The only thing that we're doing now is that we know that our outdoor temperature is somewhere between 95 and 85. It's 90 degrees. So we've taken this entire chart and we've narrowed it down to 2 rows. And all we need to do is do a little bit of math and figure out what is in between these two. They call it interpolation. And I'm saying you don't even need to worry about doing that. Because look what we're selecting from. Total capacity, 23.5 and 22.1. That's not a big difference between those two numbers. So you know what? Sometimes the lazy Tim says, I'm going to use the higher of those two numbers. Sometimes if Tim's feeling a little bit more ambitious, I might say, okay, what's a close number in between 23.5 and 22.1? I don't know. 22.8. I don't know. Don't get hung up on these details. It is not going to change your equipment selection. All right. You got to get through this. You got to get a quote out. Okay. So if you want to pick the higher of the two numbers, fine. If you want to try to get somewhere in between, fine. I would not get hung up on it. So right now, our capacity at these conditions, we've narrowed this entire chart down to 22.8. That's our total capacity. And then we would do the same thing with the sensible capacity. You can interpolate or you can just pick the higher one. I think in this case, I'm interpolating. So I'm going to take a number in between these two numbers, which are already pretty close to each other. 17.2. All right. Which means that when you subtract one from the other, our latent is 5,600. Now, how does that compare to our load? Who would install this unit? Who would not install this unit? Okay, exactly. This unit is undersized and latent, right? Undersized and sensible, undersized and total. Now notice here that it tells us, we're undersized there. It does tell us that we have a correction factor because our airflow is at 800. They're saying you can move these numbers around a little bit. If you want to go up in airflow, your total would go up by a whopping 2%. You would multiply your sensible capacity by 7%. All right. So if you chose 900 CFMs, you could make a 7% difference in this number. That's not going to be enough. Man, do not get hung up on 7%. 2% total, not even worth your time. This unit's not going to work. Okay. So what would we do? We'd have to go up from the 2-ton model to the 2.5-ton model, right? So let's do that. Now we're at the 30 instead of the 24. Same thing. We've narrowed this chart down just to what's relevant. And here's what we come up with. Now, all of a sudden, our latent load, or our latent capacity is higher than our latent load. Awesome. No humidity problems with this unit. Our sensible capacity is slightly above our sensible load. Great. And if we take care of those two, we know our total is going to take care of itself. All right. Then you'd have to look at the heating load at the same time. Next. So that's what we're going to do. We know that this is going to work in cooling. Now we have to go to the heating side of this. Our winter design temperature is 28. Lots of numbers on this chart. We're going to narrow this chart down. Out of all these numbers here, the only thing that we're worried about is, well, they didn't have a line for 28, but they had 27. That's good enough for me. All right. ACA Manual S will tell you to do a bunch of interpolation calculations. I'm telling you, it ain't worth your time. All right. Get close. Now, what is our indoor temperature, our design indoor temperature in the winter? It's 70 degrees. So I don't care what this unit does at 60. I don't care what it does at 75. I'm designing the house for 70. So now I've just eliminated everything on this chart except for one cell. That's the only cell that I need to worry about. So don't let these charts intimidate you. Just start eliminating the information that you don't need. And now we know this unit puts out 20,200. Compare that to our load. Of course, we're coming up a little bit short. So we're going to need supplemental heat, right? How much supplemental heat would you put in here? Would you put in 5 kW, 10 kW, wire nut of 15 together? We're approximately 9,000 BTUs short. Remember that quick chart that I told you guys? Here it is again. All right, so if we're 9,000 BTUs short, a 5 kW is all we need. That gives us 17. So how many of you see 5 kW units on 2.5 ton units, or 5 kW on 2.5 ton? Some of you do. If you're in a warm climate, you probably do. If you're in a moderate climate, you probably only see 5 kW on 2 ton and 1.5 ton, right? But in this case, because we did the math, we were able to get away with 5 kW. Let's say that you only had a 30 amp circuit going to that air handler. And you were looking at either having to change out that home run to the panel, or that existing home run would work with 5 kW. Doing the math here gives you confidence that you can get away with a 5 kW on this unit, and you don't have to change out that home run because you did the math. All right. If you're sizing it for emergency heat, you would need something that could make 23.2 thousand BTUs. Well, now we have a problem because now we need 7.5 kW. So it looks like you're changing that home run anyway, if you're worried about emergency heat. All right. But this is practical. This is how we're doing it. If we're a Trane dealer, American Standard dealer, this is what you're doing. All right, let's talk about cold climate heat pumps. There is a website, neep.org. It gives you a list of cold climate heat pumps. All right. And here are some of the criteria for a heat pump being able to call itself a cold climate heat pump. It needs to be at least 8.5 HSPF2. That immediately probably knocks down most of the single stage entry level heat pumps right now, because most of them are around 8.2 or 8.0. It needs to be at least 15 SEER2, not SEER, SEER2. And here is the kicker. When you look at coefficient of performance, you got to look at the specs. It needs to be able to put out at least 1.75 coefficient of performance at 5 degrees Fahrenheit. That looks like some nerdy information, right? Here's what coefficient performance is. It's how many times efficient is your heat pump? How much energy are we putting into it? How much energy are we getting out of it? And the cool thing about heat pumps is they're able to run at 200, 300, and 400% efficiency sometimes. That's what that COP is. This 1.75 means that this heat pump is producing 1.75 times the amount of heat energy than we're putting in as electrical energy when it's 5 degrees outside. And heat pumps, they're awesome when it comes to that. Cold climate heat pumps have no problem meeting this number. All right, 14 SEER, off-brand units probably have a problem with that. But a cold climate heat pump just has to meet this criteria right here to be called a cold climate heat pump on neep.org. Problem is, in the real world, that's not enough. We need to throw some additional criteria in here. All right. Here's what you want to look for. At 5 degrees Fahrenheit, you want it to still be able to make at least 75% of its rated heating. So if you got a 3-ton heat pump, when you look at the specs at 5 degrees outside, it better be making at least 75% of 3 tons, or else it's not a cold climate heat pump. It's going to let you down on a cold night. If you take a look at this Daikin unit, here's some of the specs that it gives you. notice at 5 degrees Fahrenheit and at 47 degrees Fahrenheit, there's only a 5,000 BTU drop. So this thing keeps on going when it starts heating. Its heating performance does not drop off when it gets cold outside. So that would meet this criteria here. That's a real cold climate heat pump. Just because it's 8.5 HSPF2 does not mean it's going to do this. You're going to have to look at the specs. All right. And the other thing is that it's able to turn itself down under 70% in cooling. So, you got to have its heating capacity there. And then when its cooling capacity, when it turns itself down, it needs to be able to go under 70%, or else it's not going to turn itself down enough to meet manual S on a really cold day. So take a look at this chart. Let's see here. We've got 80%. Here's what I'm talking about at 5 degrees outside. The capacity is still at 80%. We need it to be at least 75, so we're compliant there. And then on our cooling side, when it's 95 degrees outside versus what it is when it turns itself down, it needs to be able to turn itself down to under 70%. And so you would have to look at this little chart right here and see where its turn down is. Cooling rated capacity, cooling max capacity, and then there would be a cooling minimum capacity. I think it's this number right here. So for a heat pump to really be a cold climate heat pump, the main feature that you need it to be, this is how it gets that heating performance at 5 degrees, is it's got vapor injection. That's the feature that a cold climate heat pump has, is vapor injection. If you don't see that in the spec sheet, in the features of that heat pump, chances are it's not going to be able to heat over 75% when it gets 5 degrees outside, because vapor injection is the feature that allows that compressor to do what's necessary. All right. What vapor injection is a miniature refrigeration cycle within the refrigeration cycle. It's taking liquid off the liquid line. It runs it through a metering device, and it injects liquid into a port in the compressor, so that compressor can run a really high compression ratio and not overheat. All right. And if it doesn't have that, then that compressor can't run at those really high speeds necessary to create the heat at low outdoor temperature. All right. Because when it's really cold outside, what's your suction pressure on the heat pump? Is it high or low? It's low, right? It's cold outside. But we still need to make heat, right? So we need the head pressure and the high side pressure to be really, really high in order for our indoor coil to be hot. So we need a really high head pressure, and we need it to, and we know that's going to run a really low suction pressure. We're going to have a really high compression ratio, and that's hard on the compressor unless it has vapor injection. So if your heat pump does not have vapor injection, it's not really a cold climate heat pump. It's pretending to be one, and you're not going to see these specs. The other thing that cold climate heat pumps have is a base pan heater, which means that when it goes into defrost, it's got a little heater at the bottom of the outdoor unit to keep that water that just melted off the coil as in water form, so it drains away from the unit, and you just don't start building an ice dam inside the unit where the blade starts smacking it after a while. Those are features of cold climate heat pumps that you guys need in cold climates that I don't have to worry about here in coastal North Carolina. Defrost? My unit has run one time in defrost in 3 years that I've had it. All right. These are problems that I don't have to worry about, but they're problems that you guys got to worry about like 5 months out of the year. All right. So cold climate heat pumps, just because it's rated as a cold climate heat pump at NEEP, that's a start, but you also want these other features. All right. The minimum capacity, remember we said the thing needs to be able to turn down to under 70%. To be considered a cold climate heat pump. Also, Manual S was telling us we need to be able to turn down under 80% so that we're not so oversized in cooling. They give you a chart. They're supposed to give you a chart So at 90 degrees, this is a hyperheat unit here. It will turn itself down. The minimum BTUs that this unit turns itself down to is 9,000. Here's what you start off at. Here's the max, the rated. It's around 17,000. It turns itself down to about half of that. So this cold climate heat pump can turn itself down to 50% or so. Great. We need it to do that because we're sizing it for heating. We need it to turn itself down low enough, under 70% for cooling, and it can do that. The problem is they don't tell you how much of that 9,000 BTUs is sensible versus latent. We don't know. And Manual S tells you that you need to know. But none of the manufacturers tell you that. So you've got to assume that that latent capacity is 0. That's why you need a supplemental dehumidifier. Does that make sense? They don't give you this data, probably because they're embarrassed. Or there's just so many variables that maybe they just can't like come up with one number. I know that I have tested a Mitsubishi P-Series ducted hyperheat unit during like shoulder season, and it puts out 60 degree air. How much dehumidification do you really think we're putting out at 60 degrees? Not much. All right. Next summer, when I get a full summer running, I'm actually going to quantify it because these guys won't do it. I'm going to do it, and I'll be coming out with those numbers. But I can tell you right now, from what I saw, the few weeks of cooling in October that we had, it sucks. So when these units turn themselves down to their minimum BTUs, we don't know how much of that is sensible versus latent. So, and we know that we're still going to have a latent load. So you got to have a dehumidifier to pick up the rest. All right. So you're going to need supplemental dehumidification. Other factors that affect the performance is the outdoor temperature. All right. So the difference between 75 degrees and 85 degrees outdoor temperature, not a big difference. The difference between 75 degrees outside and 115 makes a big difference in how much cooling that unit puts out. All right. So if you're working in Phoenix, Arizona, you bought a 5-ton unit, you're not getting anywhere close to 5 tons out of it. All right. In this case, this is a 3-ton unit at 85 degrees outside. It's putting out 35,000 BTUs. At 115 outside, it's putting out less than 30. Half a ton difference in those extremes. So when you're checking your equipment specs, you got to make sure you're putting in the correct outdoor temperature from your Manual J. Your entering air conditions also affect how the unit performs. The difference between 75 and 85 entering can be significant. If they keep the thermostat set at 75 versus 85, there's a big difference in how much heat the unit can pull out. Your Manual J conditions is 75 dry bulb, 63 wet bulb. All right, so you would be 75, this is indoor, so indoor dry bulb, 75 degree dry bulb, and then you would be in the 63 column. Like if it was 95 degrees outside, you would use this column right here. All right, and it does matter, but the difference between 59 wet bulb and 71 wet bulb or 85 degrees, there's a big difference in a lot of these numbers. Well, you say, well, why does that matter? Like I'm always going to be pulling in somewhere in close to the 70s in air. Why do I need to worry about that? Because if you're pulling in fresh air into your air handler and it's hot outside, that fresh air mixes with your return air, and now you don't no longer have 75 degree entering air into that air handler. You're going to have something much warmer and much more humid. So you're going to have to do like a mixed air. I use this Munter Psychro app. All right. iOS and Android use it. You would put in, let's say in this case, where we've got a unit where we're pulling in, it's a 3-ton unit. We're pulling in 890 CFM of return air, and we're pulling in 300 CFM of outside air. That's a lot of outside air. All right. But the mixed air temperature, when we're pulling in both of these air streams, we're ventilating. Our entering temperature coming into the evaporator coil is almost 80 degrees and 67 wet bulb. That's huge. All right. That's your actual entering air. So especially if you're doing like commercial jobs that ventilate a lot and you have to bring in outside air, you've got to do a mixed air calculation so that you know how that unit's actually going to run. So if you're ventilating a lot, that could be enough to throw you out of manual S compliance. You may need to pick a bigger unit just because of the ventilation on it. Make sure you're using realistic indoor conditions. So manual J tells you got to use 75 degrees, 50 to 55% relative humidity. All right, so you would use this part of the chart here. How many of your customers use 75 degrees? Do you have a few customers may use 70 to 72? So Manual J says you have to use 75. And I get it. Like I keep my thermostat at 75. I've got a dehumidifier and it keeps it at 50. It can bring it down to 45 if I want it to. All right. And I'm comfortable. And my wife is cold. She's in a blanket. But not everybody's like that. And in the real world, like for example, we do a lot of beach houses here. All right. And you've got to assume that your tenant is not going to keep it at 75. So what happens if you size the unit for 75 and they actually keep it at 70? Well, the difference between that can be the difference in the size of the unit. Now, I'm not telling you to go ahead and oversize these units, but think about how realistically that unit's going to be used. If it's a vacation rental, then your reality may be 70 to 72. And trust me, you don't want that call from the owner of that house that you just put a unit in because their renters are not comfortable, and now they're talking about returning their money. That's just a reality, like in vacation rental, that you may be forced to think about what happens when they actually set thermostat at 70 or 72. All right. ACA doesn't like me saying that, but in the reality, sometimes that's what's going to happen. So we've got to make sure that we're using realistic indoor conditions. We don't want to size units for 65 degrees inside. If we've got a customer that's trying to bully us into sizing a unit for something really out of any kind of reasonableness, we need to stand our ground as contractors. Because trust me, he's going to forget all about that when he grows mold in his house. He's going to forget all about that conversation about oversizing his unit. So protect yourself. Airflow affects performance. Set an airflow that's realistic. So don't expect an air handler to put out 1350 CFM if you've got ductwork that's a little bit on the small side and you're not being allowed to change the ductwork. All right, pick an airflow that's going to be realistic. And then obviously manual D verifies airflow. Remember, the lower airflow goes, the lower our sensible is. Design conditions. All right, so again, this chart, a lot of information on this chart, right? Can be really intimidating. I'm going to show you how to simplify it. Black out everything in this chart that does not matter. Let's say we're doing a job in Wilmington, North Carolina, 91 degree dry bulb. That means that all these outdoor temperatures, none of them matter except for these two, because 91 fits in between these two. So this entire chart, we just eliminated like 2/3 of it. Our indoor design conditions are 75 dry bulb, 63 wet bulb. Now we can start eliminating this whole section because that's our 70 degree dry bulb. Now all this is what matters. Now you only have 3 sets of numbers, 3 airflows that we need to worry about right here. All right. Now we've broken down this chart into 3 airflows we can select this unit at that will meet our specs. So the purpose of Manual S is we select our unit, but we also select our airflow, our blower speed. That's part of Manual S. We're going to pick our unit, and we also know which blower speed to tell our installers to set it at when they fire it up. Here's what I do, and we're getting close to the end where we'll take a quick break, and then Nikki will come on. Here's what I did. I like putting in my Bosch units. This is an old Bosch chart. This is old model numbers. All right. I know which Bosch units I'm going to sell. What I did is I created a spreadsheet, and this spreadsheet has my total BTUs, my sensible, my latent, my heating. I also included a few other things that was available from the manufacturer. I created this from the spec sheets of the Bosch units that I sell, and only the units that I sell. I didn't include any units that I'm not going to sell. All right. And so I know my equipment. When I do a load calculation, let's say I do a load calculation And I only work in the Wilmington, North Carolina area. So my summer and my winter design temperatures are always going to be the same. My indoor design temperatures are always going to be the same. So I do a heat load calculation, and here are my results for my manual J. This is all that I do. The first thing I'm going to look at, remember I said the first thing you look at is latent. Most important thing. If it doesn't meet latent, you don't need to go any further. I got 3,500 BTUs of latent load. I'm going to start going down this list until I find a unit that is comfortably above 3,500. That first one really doesn't count. I'm going to start going here until I find, okay, looks like this equipment matchup right here, I can get 3640 at the highest blower speed. I got to move 960 CFM, but I can get there. The next thing I'm going to look at is, does it meet my sensible? I got 22,000 as sensible. It meets my sensible. Remember when I said if you take care of latent and sensible, total take care of itself? So I'm good there. Now, could I install the system? Would this work? And my heating load is 29,000. I'm close to that. I know I'm going to throw in some strip heat. But in order to do this, I would have to use my highest fan speed, speed tap 5, and I would be at 0.6 static pressure. Could I use this unit? Like, is it compliant? Like, should I? I am maxing this unit out. If anything happens, if my static pressure is any higher than 0.6, I'm not going to be able to meet my load, right? Now, yeah, this is aggressively sizing the unit, but good God, I mean, I'm like maxing this thing out. It may make better sense for me to get moved to the next unit down, and now I can find a matchup there at a much lower blower speed where I can move that same 960 CFM, but now I'm only using blower speed tap 4. I'm not oversizing my unit. I'm just not maxing it out from the very start. And all I did, check this out. My air handler is exactly the same air handler. All I did is I matched it with the 36 instead of the 24. So, I'm just talking about the price difference between these two outdoor units. But now I'm in the middle instead of at the max. And that's what you want to consider, is you don't want to be so aggressive that you're maxing out the unit and you got nowhere to go when Murphy's Law hits. All right, let's take a 5-minute break, and then Nikki will come on, and there's some really cool products from Santa Fe that have just come out, and they pretty much kick butt from all the competition, and she's going to tell you about it. But any other questions? Now's the time to answer them. So
I got
a quick question.
All right, let me see. I've got the first one on the list. Let me hear from Douglas first, and then Sean, and then Perry. So Doug first.
Awesome. Hey, thanks. I don't know if you had gone over it, but I've done some manual loads. I'm here in San Diego, California. We have a low load most of the time, but we have a large house, right? I got like a 3,000 square foot house, but I only really need like 36,000 BTUs of cooling. And when I do a manual J on CoolCalc, it comes in at like, I need 1,500 CFM. What would be my solution for that if I only need 3 tons of cooling, but it's calling for 1,500 CFM of airflow?
How does CoolCalc know you need 1,500 CFM?
Good question.
So CoolCalc has no idea. The way you figure out what your CFM is, you have to know your equipment. All right. The CoolCalc is making an assumption that's 1,500 CFM, but you would need to look up your equipment specs and see, okay, well, let's say that we're going to put in a Bosch unit here. What I would do is, what was your total cooling load?
Let's say 36,000. Let's say 3 tons system.
Okay, so 36,000. So I start, and you guys don't have much of a latent load, so we're not going to start with latent. Let's just keep it simple. Let's just look at total. So I would start going down this list, and I'm like, okay, where is the smallest unit I can put in that's going to meet 36,000 total BTUs? Well, it looks like I'm putting in this unit right here, and it can do that at speed tap 1, 0.4 static pressure. This particular unit makes 36,000 BTUs at 1120 CFM, not 1,500. So if I know I'm selling them a Bosch, then I know that I just need to size my ductwork for 1120, not 1500. So that's one of the problems with CoolCalc. And it is an assumption. And every soft, it's not a CoolCalc problem. RightSoft does it, Conduit Tech does it. They all do it. They want to try to give you a little bit more information to try to help you. The problem is that information is based on an assumption.
What about air exchanges of the home? I mean, should we bring that into consideration as if we're trying to maybe do better filtration of the home?
Yeah,
That more air quality control.
That comes into play under low load houses. So let's say you had a 3,000 square foot house, but you only had 12,000 BTUs of load. Then you'd be worried about, okay, I'm only going to move 400 CFMs through here or around that. Am I going to be moving enough air exchanges? Unless you're dealing with a low load home, usually air exchanges kind of take care of themselves. And then you can be introducing, ventilation and filtration. And hey, the Santa Fe dehumidifiers come with a MERV 13 filter in them. So, you could introduce those things for indoor air quality, but you don't run into those problems until you get into super low load homes. That's how the math usually works out.
Got
That's
it.
a good question. And that is a problem, is that these passive houses and net zero houses, they're such low load, we don't need to move as much air through them. And it's like, well, how do you maintain the indoor health in that home? And, my answer to that is, I guess, run a bunch of ceiling fans and, churn up the air. Oh, but, ceiling fans cost too much energy. Like, I don't really, manual LLH, I need to go through that so I can be more up on the low load home, strategies. But that's a whole different beast, are those homes. So sorry, I don't know enough about it to really answer your question.
No,
Sean? Your
Hey, so
question?
so I noticed on this graph it does trend that as your CFM goes up, your latent doesn't always go. Your sensible is always going up like we would expect, but your latent not. Is that just because this is Bosch chart?
Yep. Because the Bosch is going to maintain a 40 something degree coil. And so your latent load is kind of going to flatline a little bit.
Yeah, and I noticed your heating goes up. Your heating capacity goes up as well with CFM. Is that a normal trend as well?
Yeah, because the Bosch responds to airflow. So in heating, if you increase the indoor airflow, the Bosch is going to see that in a lowered indoor coil, and it's going to say, I better speed up my compressor so that I can make some more heat. So it's just reacting to the indoor airflow.
So what if it's not the Bosch? What's the normal trend with increasing and decreasing airflow as far as your heating capacity?
Heating, the formula is 1.1 times temperature difference times CFM. So as CFMs go up, your BTUs are going to go up. More CFMs means more BTUs typically.
Okay. All right. And then do you ever, I mean, like you install Bosch, so this is not necessarily you question, but I would think, if it really got down to it, I mean, not all systems have where you can have a completely separate dip switch setting or speed tap for heating and cooling on a heat pump. So, I mean, how would you feel about someone just putting a relay in there, whether you're using, whether O's energized or not? Something like that. I mean, is that something that you could do? And then, like, worst case scenario, the board's coming after you, and can a relay in there be part of your design?
Sean, I think you answered your own question, dude. No, I mean, here's the thing. If when you have a system like a Bosch that responds to airflow, if you set up the airflow so that it runs a long time during cooling and you're in a cold climate, that probably means you're going to be undersized for heating. And that setup doesn't really work too well. So, that's the one drawback to that setup there, is that you would want high speed in heating, but low speed in cooling. And you'd have to start pulling some rabbits out of your hat to make that work. But like in our climate here at the beach where you and I are at, like that's not really going to be a thing.
Okay.
Perry?
Yeah, Tim, I just wanted to let you know I have to leave for another meeting.
Okay.
But I really appreciate everything so far. It's been very informative.
Okay. Thank you.
Can I still get a recording from you?
Everybody gets a recording this class. It'll be tomorrow in an email.
Okay, okay. I wish I could stick around longer, but thanks a lot for everything, and I look forward to attending another one.
Awesome. Thank you for attending. All right, let me make sure that Nikki can share her screen. I believe we are. All right, we'll come back to dehumidifier sizing. It's actually yeah, let's go ahead. Here's Nikki. We'll
Okay.
turn it over to her now, and I'll stop sharing my screen if I can figure out how to stop sharing. There we go.
And let me see here. I'm going to go to this one, but I have to get it started from the beginning. All right. Slideshow. Can everybody see this?
Yep.
We're good? Okay. All right. So thank you everybody for your time. I know that this isn't the most exciting part, so I will make it quick. So if you're not aware about Santa Fe dehumidifiers, the company that manufactures these units is Thermistor. We are headquartered in Madison, Wisconsin. That's where our factory is at. We manufacture whole house ventilating and freestanding dehumidifiers. We invented whole house ventilating dehumidifiers back in the mid 90s, and the brand was called Ultra Air. So Ultra Air was our whole house ventilating dehumidifiers. Santa Fe was our crawl space and basement. About 3 or 4 years ago, we combined both units underneath one brand. And that ended up being Santa Fe. So if you've heard of Ultra Air, it didn't go away. It just went underneath Santa Fe. And then we also manufacture commercial dehumidifiers, which is Quest, and then Phoenix Restoration Equipment. So if you ever heard of Paul Davis or ServPro, we manufacture their dehumidifiers as well. So we are a company that is all in on dehumidification, and the commercial units, those components are used in our residential units. So you are getting a commercial grade dehumidifier in these residential dehumidifiers. We just launched what we are calling our V series dehumidifiers. And these new units are really based on the feedback that we have been receiving from the field. And the V stands for ventilation. So we've always had a 6-inch ventilation duct on our units. And now we have gone to an 8-inch ventilation duct. And the reason being is traditionally in the past, while we provide that 6-inch ventilation duct, it wasn't always used. It was capped off. But now that ventilation duct, I would say within the last 5 years, is getting used more and more. And not only is it getting used to bring in outdoor air, but we need to measure and verify that we're actually bringing in the right amount of outdoor air needed for that home. And so what we were seeing was we were not be able to bring in enough outdoor air for the size of the home to meet the capacity of dehumidifier needed. And so people were oversizing dehumidifiers in order to bring in more outdoor air. And oversizing a dehumidifier is just as bad as oversizing your air conditioner. So now we are able to bring in more outdoor air to meet the ventilation requirements for the size of the house. So what we have is, if you're familiar with the Ultra 98, it is all now the Ultra 100 or V100. The Ultra 120 is the Ultra V125, and then the Ultra 155 is just moved to the V155. All extremely energy efficient dehumidifiers, as you can see. They hit Energy Star's most efficient for 2025. And I can't see the bottom of my screen, but I don't think I have anything. The great thing about the 100, 125, and the 155 is they are all the same size box. So when you're looking at a house and you're not quite sure exactly what size unit you might need, and you're trying to at least see if you're going to have room, for those 3 units, it's all the same standard size. And we've actually upgraded the insulation in these units to an R2 cabinet insulation, which is going to help if you put these in a vented attic to prevent condensation on the unit. Plus, it actually helps with the noise of the unit as well. So we have upgraded the insulation inside the cabinet. Now, lot of data here. I'm not going to go through all of this, but what I really want to point out here is the CFM of these units, and we will give you up to 0.6. These units have a powerful fan and really can handle up to that 0.6. We always say if you're above a 0.5 or at a 0.5 or above, you know, you really need to look at the static and what's going on. But this new powerful fan can handle that up to 0.6. And not only that, but we are the only ventilating dehumidifiers out there now that are actually giving you the ventilation rates at the different statics, because this is so important as you move in. I mean, code now is now requiring ventilation, right? So we need to make sure that we know how much that these units can do. And we have a dew point cutout that we've added into all these units, because the last thing that we want is going off of just relative humidity and driving these dehumidifiers into defrost. So that dew point cutout will prevent that from happening. And again, we do have the MERV 13 filtration that Tim mentioned. We have an onboard digital control as well as the terminal block. So you'll see here that I'm going to show you in a minute here a new remote sensor that we have. And that remote sensor can be wired to the terminal block and put into the living space. It'll have to be wired. You can go like 150 feet or so. There really is no length requirement to this remote sensor, but it does have to be wired, low voltage wire. But then you can turn the unit on and select your RH that you want. Let's say we choose 50, which is the most common. When the RH gets above 50 in the living space, then the dehumidifiers are automatically going to come on. You can run continuous fans. So if you are interested in utilizing that MERV 13 filter and getting max filtration, you can do that as well. And then this is what that terminal blocks is. We have, and I'll show you on a slide here, we have a dedicated float switch port that you can go ahead and install a float switch directly on the dehumidifier and wire it directly to the unit. This is where you're going to wire that remote sensor into. And one thing that makes this a little different than some of the other units out there is we can power a motorized damper directly from our unit, which some of the competitors out there cannot do that. We have air codes. So for some reason, if the unit is not functioning, these are critical errors. We don't want to be sending errors for minor things that truly aren't affecting the operation of the dehumidifier. What we care is about critical errors. So you'll be able to figure out based on these buttons lighting up exactly what's going on, which really is going to minimize your interaction with our customer service and service team to be able to figure out what's going on with the unit. Here's that new remote sensor. It's a 2-inch by 2-inch little white sensor. This can be painted as well. Again, low voltage. Oh, we say 100 feet, but I know it can go longer than that. And you know, the accuracy of this sensor is +3 or minus, which is it's a really good sensor. And then here's that dedicated port for the float switch. So here's your drain here. If this were to start backing up, it would overflow into this port here, and you can have your float switch right here, and it automatically shut off the dehumidifier. And then we have the 205. This is a massive unit. Usually it's a more light commercial applications. The only thing I'm gonna say is the remote sensor can't be used with this one. But getting into a little bit of our efficiency, if you remember our old units, we had a 105 at one time, the 155 and the 205 that we had before. There was a heat exchanger inside these units. And basically what we did is we pre-cooled the incoming air off the coil, the evaporative coil here, and we were able to drop that air temp, basically pre-cool it, condense it, get it to dew point faster, condense it, remove more water using less energy. But these were big units. And basically what we've gone is to this, what we are calling eco technology, which is efficiency capacity coil optimization, which is a series of coils that basically are doing the same thing. We are using this pre-evaporative coil here to pre-cool the incoming air, which is going to drop that temp 10 to 15 degrees. And then the evaporative coil, another 15 degrees below dew point to extract that as much water as possible. So basically we've traded that big heat exchanger core for a series of coils. These are all dual coated coils that are very effective. And as you can see, this is what the old unit looked like, the 155. The new 155 is 40% smaller than the old one. So we can get a bigger dehumidifier into a lot smaller spaces now. And just to go back to that ventilation, to show you why we did this. So if we're looking at, ASHRAE 622 2025, which really is not that much any more ventilation than in prior years, but this Ultra V100, and I'm saying a 2,200 square foot home with three bedrooms is going to need 96 CFM. The Ultra V100, we have no problem, even at 6 inches of 0.6 inches of static, being able to meet that ventilation rate with this unit. Our old Ultra 98 unit, there was no way above 0.2 inches of static that we were going to be able to meet that ventilation rate. And then Honeywell's got some units out there. They give you their ventilation rate at 0.5, which is about 50 CFM. So not going to be able to meet it. Plus the new 62.2 requirement, 2025, requires MERV 11 filtration in your ventilation. So Honeywell comes with a MERV 8. And the same with the 125. Another scenario, 2,800 square feet, 3 bedrooms, 114. We just couldn't do it with our older units. And now, when we have the V25, we don't give 0.5 inches of static. That's why it says not available. If somebody needed that, I could get it for you, but we do the 0.2, 0.4, and 0.6. And again, Honeywell at a 120 is not going to be at 60 CFM at 0.5. You're not even going to come close to be able to hit in that ventilation rate that you need. So again, we didn't want to oversize dehumidifiers in order to meet these ventilation requirements. So we do come with a 6-year warranty, peace of mind warranty, best one in the industry, 5-year full replacement, no questions asked, with an additional year parts. And we just launched this new dehumidifier performance calculator. So it's on our website. There's the link down here for it. But you can go in and choose your model of dehumidifier and put in your own conditions, and it's going to give you the performance of that dehumidifier. What you need to understand is a 100-pint dehumidifier is 100 pints at 80 degrees and 60% relative humidity. When you start lowering the temperature, it's going to lower the capacity of that dehumidifier. And we truly want you to understand what this dehumidifier is providing you for dehumidification so your jobs are successful. And that's all dehumidifiers. That's not us. As that temperature lowers, the static increases, you're going to lose capacity from the dehumidifier. And that's what I got for you. And I can stop sharing. We do have on our website, if you go up into the right corner of the Santa Fe website, it says Partner Portal. If you click on that and you just register, which basically is going to fill out some questions and register, you'll get an email. Look in your spam because it's going to have you change your password. But we've got all kinds of tools, webinars, resources in that Partner Portal for you to utilize as well.
Thank you, Nikki.
Yep.
That calculator that you just showed us, where is that in the Partner Portal?
It is on the website, and right now it's we just launched it, so it's kind of hidden. But
Okay.
if you go into the search and put an app, APP,
Okay.
the first thing that's going to come up is the page that I put that. And maybe when you do your follow-up email, you could put the link to that performance calculator
Okay.
in
Yeah,
there.
because that's awesome. That's new. I'm actually going to be. I got to
I
change my.
emailed that to you today.
Yeah, I'm gonna have to change my heat pump summit presentation because I'm covering that, and now there's a tool. So
Yep, there is a
I'm
tool.
glad we
Yep.
did this class
And
because
you can compare it.
yeah.
You can have one and then it'll say add dehumidifier, and you can choose a different
Oh, that's
dehumidifier
cool.
below it. And so you can compare different
Yeah.
dehumidifiers and what you're going to be able to get.
Yeah. Well, man, that was awesome, and that almost that pretty much renders some of my slides even here a little bit irrelevant. I'll just go over a couple of things here. Thank you, Nikki. I'm just
Yep.
going to share. So, dehumidifier sizing. This is an old slide. This is their older models. I did write an article a few years ago for HVAC school, a lot of the lessons learned and stuff is still relevant here. Santa Fe improving the performance of already a great performing dehumidifier changes things a little bit. A couple of things we want to think about as we're starting to remember when I said that we want to seriously consider supplemental dehumidification, especially cold climates, because we don't know what the latent capacity is of heat pumps when they start turning down. The manufacturer doesn't give us that information. Decoupling the latent load means that we're going to hand the latent load now over to the dehumidifier because we don't know how much the AC is going to contribute to that. So if you go on this website to figure out what your peak dehumidification conditions are, so when we do a manual J, what we're doing is we're designing the HVAC system, the furnace, air conditioner, heat pump. And the heating side, we're designing it for an outdoor temperature of this 99%. For cooling, we're designing it to this temperature, these conditions right here. But here's what's interesting. Your manual J design day is rarely your most humid weather. The hottest day of the year is rarely the most humid day of the year. The most humid day of the year is rarely the hottest day of the year. That's what this section. So when you go to this website here, you can click on a map and you click on the whatever city area that you're doing the job at, and it will give you a list of weather stations around that area. You pick the weather station that is closest to your climate. Usually it's the closest weather station to you, unless you're near a really big body of water or near a mountain. And then the closest weather station may not be your same climate. You need to be really careful. Other than that, if you're out in the middle of, flat ground, you can choose this closest weather station will probably be okay. You're going to get this chart right here. This is what you're doing your manual J for. When we're looking at the dehumidification load, we're looking for this lower row right here. Okay? That's your cooling. That's your manual J cooling. For example, Wilmington, North Carolina, I'm at 91.2 dry bulb, 76.9 wet bulb. But notice what my peak dehumidification is. When I do a conversion using the calculator, that's a 72-degree dew point. That's oppressive humidity, but it's a Carolina coast. We know we're going to get that. But notice the dehumidification. The dew point on our peak dehumidification is almost 77 degrees. Now, that is some swamp butt weather there, okay? But even more importantly is notice what my outdoor dry bulb temperature, that's MCDB, that's mean coincidental dry bulb, it's 77 dew point on an 82-degree day. How much air conditioning do you really think I'm running on an 82-degree day? I'm running some, but do you think if I had a cold climate heat pump in here, it would probably be running at its part load, its minimum capacity? And then the manufacturer of that cold climate heat pump, or most inverter heat pumps, don't tell me how much of that minimum capacity is latent versus sensible. So I have to assume that it's zero, or else I may have a problem, especially as a contractor. And so what I need to do is run another calculation. I pretty much do another load calculation, and I figure out what my latent load is at these outdoor conditions. Because it's at 83-degree dry bulb instead of 91-degree dry bulb. All right. And so what I come up with, let's say that my dehumidification, when I do that other manual J using these conditions, I come up with 3,400 BTUs, and that's actually pretty low. All right. That's what the latent load is for my house, but my house is very tight, and the only latent load that there is whatever's coming in through the ventilation. Here's how you figure out how many pints per day of dehumidification you need. You take your latent load and you divide it by 1,054. If you want to do back of the napkin math, you can just divide it by 1,000. Move the decimal point 3 spots over. All right. And then you're going to multiply that by 24 because you're talking about pints per day, not pints per hour. So you do this, then you multiply it by 24, and you're going to come up with 77 pints per day. That's your dehumidification load. That may not be the dehumidifier you put in, but we came up with 77 pints per day dehumidification load. I don't know whether this is still relevant because, but manual S dehumidifier, they say should be a size for at least 85% of the latent load. I'm telling you that if you're working with an inverter heat pump, you may need to get closer to 100. That's just a reality of what we're seeing because we're not, our heat pump is not contributing to the latent load the way the old R22 12 SEER rattlers did. Those things ran some really cold coils. Now these new high SEER units are not helping out much. Dehumidifier performance, I actually pulled this today from, this is what Nikki just shows you. Pull some, this is new dehumidifiers out. Again, our target pints per day was 78. Look here at manual J, conditions 75 and 50%. The Ultra V125 would be the, give us 83 pints per day. And actually, it's kind of cool. They give you your latent capacity. Not everybody does that. So you may not even have to do that conversion anymore. At Santa Fe, they're giving you your latent capacity right here. So you could take your latent capacity that you got from your load calculation, which was like 3,400 or something, and you can put it in here. The Ultra V100 may get it. I get a little bit more confidence if I put in the V125 to get 78 pints per day. All right. And these are realistic conditions. The dehumidifiers are rated at these conditions here. 80 Fahrenheit, 60% relative humidity. This is what the government mandates they rate them at. This is not Santa Fe trying to cheat the system. This is like AHRI, but for dehumidifiers. All right. So yeah, it makes 125 pints when you got a lot of water in the air. But when you put it in an actual house that is not a sauna, there's less water to pull out of the air. Sort of like squeezing an orange. If you squeeze a nice juicy orange, doesn't take that much energy and you get a lot of juice out of it. But what happens the second time you squeeze it? You got to squeeze a little harder and you don't get as much juice out. Same thing here. That's Nikki's slide. So manual S, once you've done your manual S, this is what you should know. You should know what equipment model number you're going to put in or you're going to propose. Because you've done the math. You figure out which one is in between the bumpers that Manual J has prescribed. You're going to also know your sensible latent cooling capacity and your heating capacity. Okay, that's what Manual S gives you. You should know what your cooling airflow is going to be at that capacity. You may have a different heating airflow. You're going to have a cooling airflow and a heating airflow. All this is when you look at the spec sheets and you're matching the specs of the unit to your load, this is what the information the spec sheet's giving you, your capacities and your airflows. But you're also going to know what static pressure you're going to get those airflows at. I should have put that on the slide. It's not there. But the next thing that we have to do now is build a duct system around our unit. We know our capacity, we know our airflow, we know our static pressure. Now we need to build a duct system that we can move that airflow at that given static pressure. If we put in too small of a duct system, our static pressure is going to be higher, our airflow might be lower, and our capacities are going to be lower. Now all of a sudden our unit can't keep up. So that's where we go next is Manual D. We're going to build the duct system around the airflow capabilities of the unit and the airflow requirements of the design. And that's what we're going to be getting into next time with in another month with Manual D. Here's another thing I asked you guys to do. You know how I make those funny roast videos? Well, sometimes the people that I roast find out what my company name is, and then they leave fake Google reviews. So that drags my Google rating down. So for your entertainment, my Google rating sometimes takes a hit. So what I'm asking you to do is to leave a positive review to help counteract the bad reviews that Google does nothing about, the fake ones. All right. Um, so if you don't mind, if you've enjoyed this class, please leave a review. I am running the Manual D class next month in December with Chris Hughes of the Energy Conservatory. All right. I'll be posting that. I see you got a quick question. We're done. Okay, definitely. But yeah, I will be posting social media on that, probably starting tomorrow. I always like to conclude on this slide. A properly designed HVAC system is safe, healthy, comfortable, and efficient. If you don't do a good design, you could sell them a 22 SEER unit, but if that unit is grossly oversized, it's like putting monster trucks on a Prius. Are you going to get 50 miles of the gallon? Is that going to be a very efficient setup? Of course not. All right. So, there's a reason why Manual J, Manual S, Manual D work. Once you do it enough, it's sort of like putting in the reps. You get really good at doing it, and then you can start learning the shortcuts that are still responsible to take without cutting corners. And that brings us to the end of the class. So just some housekeeping. Tomorrow, you'll get an email with a link to view the class. It'll probably be another link to leave a review. It'll be some links to Santa Fe stuff, especially that calculator. I'll put that in there. And then you guys will be able to see the recording of this video. And please don't share the links with anybody because, you paid for the class, they didn't. And I would appreciate that. So I'm going to stop sharing my screen. And the next thing we're going to do, we now enter into happy hour, which means I'm going to go grab a Guinness beer. I'm going to come back. We're going to answer some questions, ask some questions, tell war stories, all that stuff. And I think we have a couple already in the chute. So give me just a minute. I'll be right back.
Nikki, this is Rick Kinsel. Can you please tell me real quick, is the static pressure total external static or is it supply static?
So it is, well, it would be the total static. So if you're going to put it just on the supply side, it would just be the supply static. But if you're going to pull from the return and tie into the supply, then it's going to be the total static.
But I'll be pulling in from the home and the outdoor. So am I taking my return static and the supply, or do I take it just the supply?
Usually if it's a dedicated return to the unit, it's minimal static, hopefully, but it is total static.
Okay, total external static. Thank you so very much. I appreciate your help, Nikki.
Yeah, that's the hope. The hope is that.
And congratulations again on your honor. It was really great seeing that.
Thank you. I appreciate it. And it's good to hear from you.
Thank you, ma'am.
I am actually going to jump off. I am not grabbing a beer. So if anybody has questions here, I am going to. Tim, I was just telling everybody I'm going to jump off here.
Yep.
Thanks. But I was going to try to figure out how to. I'm going to put my email address in here in case anybody has any questions. Please feel free to reach out to me. And then I did send you that link, Tim, to include earlier today. So I appreciate everybody. Thank you. Have a good evening.
Good seeing you, Nikki.
Yep. Thanks.
All right. Let's see. I think I saw in the chat. All right. So I've got so I'm going to take them in order that they came in. So I've got someone from iPhone. If you want to unmute and ask your question.
Yeah, that might be me. So looking at that map to find like your climate, I'm kind of in between mixed climate and cold weather. So I'm in Philly. So it makes it a little bit harder for heating and cooling wise am I going off like the cold weather and then the hot weather or mixed climate weather, I should say? One for cooling, one for heat.
Yeah, that's that map was very, very general. I'll show you how to use that. So I'm going to share my screen real quick. Let me bring up, hang on. Let me share this screen right here. And before I share it, I want to make sure. All right, share my screen two. That's that ASHRAE Medio website.
Oh, okay.
All right. So I'm going to click on map. And I'm going to zoom in to America. And then I'm gonna right click. Well, first of all, I need to make sure I'm choosing I think that's American, and I'm gonna choose, ooh, they got 2025 now. That's very, very new. They just updated all the weather stations. Nice. I've been waiting for this. So we're gonna click on 2025 weather data. We're gonna right click on Philadelphia. Now it brings up the closest weather stations. So it probably doesn't matter which one we choose because, but
yeah.
I mean, which one of these do you think would be closest to like?
Oh, I can't. A.
Like, are you North Philly, near Northbound, or
I'm southeast, so it's either
Southeast.
A or B. Yeah.
All right, so maybe the closest one is like this B.
Yeah, B's fine.
All right, so click on B. We're going to scroll down here, and your winter design temperature is 18.7. Now, does it get colder than 18.7? Absolutely, but it doesn't stay there for more than 1% of the time, is what they're saying.
Right.
Your cooling is 91, and this is the
That's more like you.
Yeah, you guys get every bit as hot and humid as we get in the South, but you also get cold weather, so that's a challenge. I would say you're right there on the cusp of a cold climate. There's not like one number that says that you're either a cold climate or not, but what you don't want to do is get like that call that your unit can't keep up. So,
that would be my follow-up question would be for designing mini splits. Would I be going to like a hyperheat?
Yeah, definitely. I mean, because when you look at,
I was curious.
Yeah, when you start looking at, I mean, the real question is, or the real answer is, look at the specs of your unit, see what it does at, around 18. Yeah, you're going to look at your performance specs and see where the drop off is. But I'm going to tell you, normally, you're going to start seeing that drop off below 20 degrees on your typical, 16 SEER heat pump. That's just kind of where they all kind of drop off.
Right.
So yeah, you'll start seeing that. And if you don't use a hyperheat unit, then you got to think about your supplemental heat.
Yeah.
How much you're going to really need. So,
all right.
Yeah, you are in an interesting area. Where I'm originally from is Greensboro, and this is about our summer conditions, and our winter is about, I think we're at 22 degrees, so it's just slightly warmer than that. And I was putting in hyperheat, especially if I didn't have strip heat. I was putting in hyperheat heat pumps. I got burned one time not putting one in. Made that mistake one time. So
I do. I've done a lot of mini splits over in like Conshohocken area, and we usually put in like the cold weather, the cold climate ones.
Yeah,
Fujitsu, Bryant versions, different ones, but
all right. Oh, good to know. All right, thank you.
Yeah. Let's see. We got Aaron Barnett. Can you talk a little bit about how to integrate dehumidifiers into air handlers They stand alone or do they replace the ERV? Okay, I actually have a slide for that in another presentation. So let me open that up. Give me a second. I'm doing for the, I don't know if you guys have heard about the Heat Pump Summit. Has anybody heard of that? It's coming up in near Boston. I got asked to be a speaker there, which was cool. But let me let me pull up my Heat Pump Summit presentation, and I got a slide that will answer your question. All right. Where did everybody go? Okay, here we go. You guys can still see my dry houses and wet climates screen. All right. So, let's see, where's my, here we go. Ventilating dehumidifiers. Let me just start this slide. Okay. So typical ventilating dehumidifier. This is how you conduct it. You either tie into your HVAC return or you can put a dedicated return on it, whichever is easier. If you've got high static pressure in your ducts, like if your total static pressure exceeds 0.5, you may want to think about trying to run a dedicated return as long as it's not too long. It's, but you know, if you've got a normal static pressure of under 0.25 on either side, then yeah, especially these new dehumidifiers in Santa Fe, they can overcome that. So you're going to run your return, either a dedicated return or tap off your return plenum on your air handler. Your supply is going to merge back into your supply duct. And you're going to try to merge it in at an angle. Get one of those angle boots where you're merging two airflows together. This airflow is merging in at an angle with this airflow. If you don't, you can create static pressure because you got both those airflows crashing into each other at like an intersection. So sort of like when you're driving, what's easier to do, merge onto a highway or approach an intersection and then make a right turn? You know, so same thing with airflow. If you can merge it in at an angle, you've just reduced the static pressure that dehumidifier sees on the supply side. Now you don't have to worry about it, but like with older dehumidifiers where they had the 6-inch connection, you would want to upsize the fresh air duct to at least an 8-inch. Because if not, you're not going to be able to pull the amount of air that you're probably asking it to pull. You would do a motorized fresh air damper. Okay. So you'd have a fresh air damper normally closed, takes 24 volts to open. You got to do something on the supply side. Because let's say this dehumidifier is not running. What's to prevent supply air, static pressure from backtracking through this unit and either turning this whole thing into one giant bypass or like dumping supply air out the fresh air duct? You don't want that, right? Well, hopefully this damper motor would be closed, the unit's not running, but you wouldn't want to turn this into a giant bypass. So you either put a gravity backdraft damper that's spring open. The problem that I found with those is that they don't open all the way even when the unit's running. You ever want to, get one and stick it on the outlet of your dehumidifier and plug in the dehumidifier, and you'll see it'll only open about halfway. Maybe the ones that I were using were cheap and the spring was too strong. I don't know, but they sometimes don't open all the way. That's why I like to put a motorized damper because I know that thing's going to open all the way. All right. And then at that point, like if you're running a inverter unit, that's really, really nice because the fan's going to be running almost all the time. And so you're always going to be distributing dry air through the house. If you're in a cold climate, you're hopefully putting in a cold climate heat pump that's going to be inverter driven. Hopefully your blower is going to be doing something. You're going to be producing some kind of heat on a really cold day almost continuously if you sized it right. And that way, if it's 0 degrees outside, you're bringing in 0-degree air. Just make sure you've got your ducts insulated because they will sweat. And when you dump that 0-degree air, hopefully it's mixing with 100-degree air here. And so the air coming out on everybody's necks is not feeling too cold. But you got to think about that. What happens when we ventilate on a really cold day? So yes, you can make a dedicated supply. You don't have to put this in your supply duct. But where the heck are you going to supply 0 degree air back into a house on a cold day? I mean, there's not a lot of places you can do that. It's going to piss somebody off, right? So that's why I like to put in the supply duct. That way we can kind of diffuse that cold air. So your HVAC fan can run at a low speed if it's inverter driven, if it's running heat. Usually people don't like to feel their blower running all the time in the wintertime if it's not making heat. That feels drafty. So you may not want it to do that in the wintertime, but if you're running an inverter unit, probably you're running low speed and your compressor's running low speed and you're making heat pretty much continuously during cold weather. Your optional dehumidifier fan, you can also wire this dehumidifier, just jump fan in 24 volts, and you can run this fan all the time. Okay. The benefit of that is that when it's not ventilating, we're recirculating air through the system, and we're always pulling a little bit of air through this MERV 13 filter. I do that a lot. When you do that, now all of a sudden you don't need a motorized damper in here, because you're never going to backdraft unless somebody unplugs that dehumidifier. And what I'm afraid of is if I put in a motorized damper and its entire life it stays energized, at some point that damper is going to fail. It's going to fail close, and I've just created a problem. I also don't want to use a backdraft damper because I don't want the entire life of that dehumidifier for the backdraft damper to only be open 50% of the time. So what I do is I put a hand damper in here. And if you're going to unplug this dehumidifier for whatever reason, you close the damper. It's one idea. That depends on what your comfort level is. I'm not saying you have to do it that way. That's just my thought process. A spring-fed backdraft damper kind of is a nice middle ground. I don't like how those things, when they open, they only open like that. They don't open up all the way. And so, you're not able to push the thing open all the way. Next time, try it. Just stick one on the butt end of a fan, and you'll watch it. It doesn't open up all the way. But those are optional. When we talk about demand control ventilation, so demand control ventilation is we don't ventilate continuously. We only ventilate when we need to ventilate. Problem is, it's not compliant with any of the standards. But the standards are stupid, and code is stupid. Why, when the occupant goes on vacation, why are we ventilating the house? And are we really expecting the occupant to tell our control, hey, I'm going on vacation for 2 weeks? They're not going to remember. They're barely going to remember to turn their thermostat back. Now we're telling it something else. No. So here's what you do. If you don't have an inspector or a HERS rater or somebody else, third party, breathing down your neck, checking back behind you, ventilating on demand, it's in the commercial world, that's what they do. They don't ventilate unless you have to ventilate. But I use the Haven. You guys have probably seen me, post a lot about Haven IQ. Here's what I do. I build in automations in Haven. When it's really humid outside, I create a outdoor air dew point lockout. Notice that here, hang on. When the dew point is above 75 degrees outside, that is swamp butt weather. I am not going to ventilate if it's over 75 dew point. Now, if you're in a climate like South Florida where it stays 75 dew point, you can't use this. I kind of know my climate. And so I know that it's not always over 75 dew point. It is for a few hours of the day, then it gets down below, 75. But you may want to consider an outdoor dew point lockout so that you're not dumping all kinds of moisture into the air. You're going to wait a little while before you bring in that fresh air. But here's some other automations that you can build in. The Haven allows you to dehumidify based on indoor dew point and not RH. So it does not matter if the thermostat is set to 82 degrees. It is still going to dehumidify based on dew point. If you're only looking at RH, 82 degrees and 50% relative humidity will grow mold. But if you're looking at dew point, that's an absolute number. I always use a non-Wi-Fi dehumidistat. that's set to 60%, just in case like they decide to change their router password. Now all of a sudden they don't have a dehumidifier. That doesn't work for me. So I'm gonna get another little cheap dehumidistat. I'm gonna set it to 60%. I'm gonna put it like in the return grill behind the filter, so nobody monkeys with it. They don't even know it's there. And that is my backup in case my Wi-Fi goes out. That's just Tim DeStasio's paranoia for my peace of mind. All right. But notice, yeah, so that's kind of what I do. That's how you duct it, and this is how you control it. I set a indoor dew point set point for dehumidification at 52 degrees, and I set my outdoor air damper. That's just one of my automations. This one right here will start ventilating if my CO2 gets out of the good range. I've got other ventilations built in based on VOCs. You can do radon, you can do NOx. I don't have a radon problem here at the beach because we don't have any granite that's going to off-gas uranium. But if you're, near the Appalachians, you're going to have a radon. You're going to want to look at radon. So build an automation. So it's pretty much this automation except for CO2. I've got one for VOCs, and you can build one for radon and NOx. So saying that you just build multiple automations, and if any of these trigger, then you're going to ventilate. And then this is my dehumidification. I just set it 52-degree dew point, and it just, as long as it's as long as it's around 52 degrees dew point, I know I've got a safe house. All right. And then yeah, so talking about ERVs, so the problem with an ERV is they only remove 65% of the latent load. When you look at the specs. So that means 35% of the moisture is still getting in the house. So you're always going to have a net gain of moisture. So you're still going to need a dehumidifier. So my whole thing is, if I still need a dehumidifier, why don't I just make that dehumidifier a ventilating dehumidifier, and I don't need an ERV.
Right. That was kind of where that question was going.
Okay.
It's like, does a ventilating dehumidifier essentially replace an ERV in your mind in wet climates? And it sounds like the answer to that is yes.
Yeah, I don't think, especially the limitations to the ventilating dehumidifier before the V series came out, as she showed you, was the limitations in outside air that they could physically pull in. Now that they built a dehumidifier that you can pull 150 CFMs into a 125 pint dehumidifier, I mean, there's not a lot of houses that need more than 150 CFMs, especially when you're ventilating on demand. Like these ASHRAE 62.2, whereas how we calculate that ventilation rate is, I mean, it's like worst case scenario. Like, what are you doing in your house that you need that much fresh air? Like, are you raising pigs? And like, what are you doing? I don't think we need as much air constantly that we need. Like when we need it, we need it. But I think 62.2 in a lot of cases is too much air. So yeah, there's really no reason for an ERV in a southern climate anymore. People say one place where you would need it is in a super airtight house, because 150 CFMs being pumped into a house. If you don't have anywhere for that air to exfiltrate, then you're not going to be able to pump that air into a house. So like with my house, like 150 CFMs of fresh air would be a lot of air. Like, it would I would have trouble closing my door, my front door.
Yeah.
So yeah,
A
super
fellow
tight
that works
houses. But yeah, unless you're in a super tight house, ventilating dehumidifier for the win every day.
A fellow that works for me is building a passive house in Austin right now, about 3,500 square foot. So
Yeah.
he's doing both. And I work in the Pacific Northwest, where dehumidification is a complete non-issue.
Right.
And so I'm trying to learn about dehumidification, how that stuff works. And it sounds like in that case, that's probably the right setup. He's got an ERV and a ventilating dehumidifier.
Yeah. I mean, when you choose to build a passive house, you've decided that you're going to spend money like on really minute things. You've decided that you're going to throw in a bunch of mechanicals into your house. And yeah, you've made several decisions that maybe people aren't aware of. Like everybody wants to do passive houses and still till it's time to do passive house things. Like you can't even turn on your kitchen fan without sucking the gonads out of your house. Your kitchen fan turns into a blower door with a passive house. And so it's like, all right, now we need a makeup air unit. So we need an ERV, we need a dehumidifier, and we need a makeup air. And you know what? The architects that design these passive houses, they never put any space for mechanicals. Like, where do you want me to put all this stuff at? Yeah. So anyway, that's my long-winded answer.
Awesome.
Michael is next, I think, right?
Yeah, I noticed you didn't use any of like the Manual S speed sheets. Is that because you built your own?
The reason why is that the Manual S speed sheets are for the old Manual S, and unless they've updated them, I have not heard that they have.
Well, and I haven't seen any either, and I was just curious if they were gonna
Yeah,
because
so the old Manual S, I mean, I think they are, but the old Manual S was really, really simple, and you could use a speed sheet, and I would have taught off of that. The only problem is the Manual S speed sheets also make you do like interpolation 4 ways. Like your temperature, your outdoor temperature, your indoor temperature, and your airflow. And you got to interpolate all those to get that exact number. And I'm just saying, like, you don't have to be that exact,
right.
And so
Well,
it's,
yeah, there's one tab. If you could just dial that in like the My Carrier app, you could
yeah.
put that straight in.
Oh,
But
okay.
especially when it comes to supplemental heating, I didn't know if they were going to update that because I and you answered a question I didn't even know I needed to ask about how they oversize the heating load. Oftentimes, I have a lot of basements here, and so the heat load looks way higher than the cooling load, and so I fret about getting enough supplemental heat in there. But
Yeah.
if I only have to hit 95% of that, and I may just make my own sheet like you did, just so I can plug those numbers in and make sure I satisfy it.
Yeah, if you're selling units, get to know your unit specs really good and make a cheat sheet only on the mod. Another thing that I do is, you know how you can sell a 3-ton matchup and you can sell it with a 3-ton air handler or a 3.5-ton air handler or a 4-ton air handler. Unless you have space constraints, always just start selling the 4-ton air handler with the 3-ton unit. It'll give you a bump in SEER. It'll give you better dehumidification. And like, what's the cost difference between the 3-ton and the 4-ton air handler? Like $100?
Minimal, yeah.
Yeah, and it just performs better. Now I totally understand, like if it's in a closet, you can't fit it, whatever. But like your standard matchup, always oversize your air handlers if you can. It's better. Let's see what else we got here. We've got Kane.
Yeah, so my question doesn't really have much to do with what we went over today. It has more to do with what we did a couple weeks ago on the Manual J.
Okay.
In that meeting, anyways, you mentioned that your house only uses 1.3 tons. It's pretty efficient, and you end up having to use your ceiling fans to move air because your unit doesn't run super
Yeah.
often.
Yeah.
Well, I was thinking about this the other day. With your system being all variable speed and everything, why not just run your continuous fan at a really low speed to circulate air throughout the house? You might have mentioned that, but I've had 8 concussions and I forget stuff pretty easy.
No problem.
So,
So, I kind of do. So I've got on my Haven, all my automations, what I just showed you guys there on that slide, that's a fraction of the automations I've got set up on Haven. So, um, any little thing, any little indoor air quality event, and my air handler turns on. So my air
okay.
handler ends up running a lot anyway. The thing is, like, I'm not throwing the air across the room the way I designed the duct system to. I designed the duct system for 2.5 tons, 2.3 tons of airflow, whatever
I
that
think
was.
you did mention this. It's
Yeah,
coming back to me
and
now.
now I started reducing the airflow because I'm like, dang, I don't need all this. And now my air, unfortunately, comes out sort of like a drunk uncle out of a taxi, just out of the vents. And so I kind of need like a ceiling fan to churn things up. I
Okay,
got
I
I got six
I
by
remember you
12s,
saying
man.
that.
I got 6x12s and 8-inch supplies in like my living room, and there's just no velocity there anymore. But
Okay.
I designed it for what I thought the load was going to be, and it turned out it wasn't anywhere close to that.
All right. Thank you.
Yep. Let's see here, John. With an in-home dehumidifier, most that I've seen Minnesota have been return to return. I forgot where I heard it, but maybe Adam Muffet somewhere. I heard that some people run a dehumidifier from return and dumps into the supply. So the AC does its job, but what consequences does it have on static? So if you run the return of the dehumidifier, so I guess you're saying is you're pulling your dehumidifier return from either the ducted return or its own return, and then you're dumping the dehumidifier back into the HVAC return.
Yeah, so basically you suck out of return, dehumidify it and filter it, I guess, and then dump it back into supply.
That's the preferred setup, is that you would dump into the supply duct the way I showed in that slide there. Now you have a dehumidifier and an air handler that are now competing for the same duct. And so you would not want to do that if that supply duct already has high static. You would want to, yeah. And so at that point, you would the preferable option is to fix your ductwork. Because if you dump the dehumidifier supply into the HVAC return, what's nice is that your air handler return is going to suck the air right out of the dehumidifier, right? But what's not so nice is that if the AC is running at the same time as your dehumidifier, you're throwing hot air on the AC coil and you're now derating that coil. You remember when we said that your entering air conditions matter on equipment performance?
Yeah.
Well, if you're dumping 105-degree air onto that coil, then you're going to mess with that coil performance. So you could do that. If I were to do that, I would probably put in some kind of lockout that whenever the AC ran, the dehumidifier could not come on, so that I wasn't messing with my AC performance when the dehumidifier came on.
Well, none of that is common in Minnesota. It's all return to return, and I think in the instruction manual it says the dehumidifier return just has to be 8 feet upstream of the dehumidifier supply, also into the return.
Yeah. I know I know people run it like that. That's my concern is, and it may be that you guys don't really run into many situations where your dehumidifier and AC are running at the same time. So you don't have to worry about it. But like in my climate, that's an absolutely plausible situation that I'm running dehu and AC at the same time.
Yeah, I mean, we get pretty humid air, and then Minnesotans are the type of people where because it went below the thermostat set point overnight, it means that it's time to open the windows. So then they just invite all that humidity in the
I
house.
gotcha. Yeah.
And then naturally they subtract a half a degree out of the house, but they've invited in 99% humidity. And then when 3 o'clock rolls around, when the sun starts baking the house, it's high humidity and high temperature, and then it just never satisfies until like 9 o'clock at night.
Gotcha. So let me bring up something real quick. Let me pull up the V100 installation manual, and I want you to tell me which of the installation that you're talking about, just so I understand what you're asking, because there's a chance that I'm still not answering your question. Let me look at these. Here we go. Okay, let me share this screen here.
I mean, when you went through your other stuff, you pretty much covered what the preferred method was of everything. So like I wrote down half of what you said.
Yeah.
But
so which one of these is it? Which one of these represents what you guys are doing in Minnesota? You got dedicated return. Don't worry about the fresh air. That's not relevant here. Are you dumping your supply into the supply duct?
as far as all the ones that I've seen, they're either sitting in the basement with no ductwork and it's just doing itself, or it's pulling from return of the ductwork
Okay.
and dumping back into return 8 feet downstream.
So it would be
Like that, except return. There you
kind of
go.
like this.
Bottom one.
Yeah, right here.
Yeah.
Yeah, so I mean that is an accepted installation. And what's nice about that is that you don't have any static losses right here, you know, because you're getting your air sucked into the return of the air handler. You know, just the only thing is you are dumping. See, check damper is not in place. HVAC fan must turn on. The dehumidifier is in operation. So you do have to run the air handler at the same time. And just again, my concern is what happens when we have a wet coil here. Are we dumping, you know, hot air on that wet coil? That would be my concern. And that may not be, you know, a situation that happens with you guys. So, yeah, I'm actually doing something with mine that's not even on this chart. I've probably voided my warranty with Santa Fe, but if you guys follow me on YouTube, I got this series Hot Rod Bosch, and I've got my supply duct of my HVAC feeding my dehumidifier return. My dehumidifier is turned into a powered bypass duct essentially, and I've got all these Haven controls built into it, and I'm doing some weird stuff as a, I don't know, experiment. But all right, let's see. I also see Sean. Did you have a question again? Sean may have hopped off.
Yeah,
Oh, there you
sorry,
go.
I
Okay. Yeah.
didn't turn my mic on. So the first thing I want to mention, like you said, dumping it in one area of the home. I've had where customers complain that something's going on with their floor. You know, I don't know what the exact construction material of the floor was, but that's another drawback is it'll get too dry in that area if it's not wide
Yeah.
open. And then my other thing is, so basically my questions were all the same, you know, questions about the dehumidifier and how to duct it.
Okay.
I'll try to be pretty quick with this, but we've got a trouble call. So is this guy, I told him to call you, and I think he didn't want to spend the money, but it's this real old house in like Sunset Beach, and he had a 3-ton small house, very small house on pilings. He had a 3-ton downstairs. We ended up replacing it and then putting in a dehu. And he said all the previous summers it was cold. It was always, you know, comfortable temperature wise.
Yeah.
But you know, he had a humidity issue, and he just had a standing like dehumidifier like draining into his sink or something.
Mhm.
And we ended up putting in a ducted dehu, but now he's like, it's worse. It is warm in there and doesn't feel good. So if I do a BTU output calculation on my air handler, I've got like 6,000 more total, you know, BTUs without the dehumidifier running. And it's currently really the only way we could install it non-invasively. It's in a like kind of garage area under the house. So, and then it's like ductboard that's all enclosed except for a little bit of it. So we've got straight from the return right in front of the air handler going to the supply right after the air handler. And I guess my question is, so my BTU output is like, it's like the air handler's doing so much worse because it's increasing our static from I think 0.5 to 0.6, and that's, you know, affecting our CFM. So therefore our output calculation is going way down. And you know, I'm going back there. They, you know, removed the underpinning of the house or whatever. I don't know if that's the right word. So we could look at the duct board, but we're sure it's leaking. We know it's leaking. But you know, I was thinking to avoid, and this might sound crazy, but to like, they're like looking at me to handle it. I'm thinking like to avoid the hot air going onto the coil, what if we just cut a hole in the air handler right under the blower? Well, no, because then it wouldn't be pulling all the way through the coil. But then you know your air handler airflow. So
I've seen people do that. I've seen
Yeah.
people cut a hole and the blower sucks it in after the after the coil. Here's what I think your problem is, because I run into these all the time at Sunset Beach. You've got a crappy envelope, and you've got a unit that runs at the same time as the DHU. The DHU is putting out at least a half a ton of sensible load. And despite all that, your envelope is so crappy that the humidity is still there. You got so much latent load on the building that even with the DHU running, it's still not enough because you can't HVAC your way out of a bad envelope. But now you've added 6,000 to 8,000 more BTUs of sensible load. So now your AC can't keep up. And now he's not, he's hot and humid. And his answer is he's got to improve the envelope. And until he gets his head wrapped around that, then there's no mechanical solution to that.
Yeah, that was my diagnosis, was to call you and have you help taking care of that. But see, like I kind of have to give him, I'm trying to give him what he wants, but I'm trying to give the company what they want to, you know what I mean?
Yeah, but if he's not ready to address the envelope, then you can't pull a rabbit out of your butt,
And I can't tell him the DHU made it worse either. You know what I mean?
Yeah, and so there's a lesson to be learned here that a DHU doesn't fix everything, especially in our climate. And just, live and learn. But yeah, right now it's like you can explain it to them like, look, we have done everything we can from a mechanical standpoint, and now we need to take care of the envelope to get you the rest of the way there.
Yeah, I think when we go and he's like I said, we're gonna replace the ductwork that is accessible. It's so terrible. Some of it's under the house, but then it goes up through a plenum into the ceiling of the first floor, so it's not all accessible. But I think I'm gonna tell him while we're there, we are looking at changing the way the return ducts, giving it its own dedicated return, and fixing what leakage we can on your supply duct. But I'm going to be honest, I'm going to say, sir, like I truly am trying to explain that please investigate the infiltration.
And you can put a relay to lock out the dehumidifier when you get a call for Y, so that you don't get that extra sensible load on a hot day. And then that way the dehumidifier just runs during the mild weather.
Yeah, and it's got an internal sensor, so I'll probably have to like break into the DHU to do that.
Oh, okay. You guys, what DHU did you put in?
So it was one Bolden's did. It was one that was like their baby that kept crying that now I'm in charge of. So
was it an Ultra series?
I think so. It's got its own built-in backdraft damper. I remember that because I looked that up when I was doing my output calculations just to make sure it wasn't bypassing.
Okay.
But I want to say I don't know. It just had a couple buttons on it. You know what I mean?
Has it got a float switch on it? It's got a float switch on it, right?
It was in a pan and it would have had a float switch. I would have said
break the float switch. That'll do it.
Yeah, true.
All right.
True.
Cool. All right.
Yep. I think that's it for me though, but you guys have a good night. Thank you.
See you, man. Casey. Oh, he said he's going to catch us at the next Zoom. All right, cool.
I'm just thinking about an SPNO relay for that. I'm breaking this float switch, and that's ingenious.
So I'll tell you something.
It would work. It would work.
Even crazier that I've done. So the old versions of the Ultra 70, they have a little built-in dehumidistat dial.
Mm-hmm.
And so I was like, great, I don't even need an external dehumidistat. The problem is if you hook up a float switch between R and DHU on it, the dial bypasses all that. So it's like you either hook up a dehumidistat and you turn the dial off, or you run the dial, but you don't have any like other controls. Like you would like run it like you were in a crawl space where it doesn't matter if it leaks. And so what I would do, I was like, well, crap, I still need to like have a float switch in this thing. So I wired the float switch to short between 24 volt and common, so that if it ever tripped, it would trip the little circuit breaker popper. Humidifier. It's a manual reset float switch.
It's a suicide switch. I like it.
But those things got a really reliable popper on there, and it would just pop it. But I was like, yeah, that's kind of a jank way of doing that.
And do what you got to do sometimes.
Yeah, man. Job was already in the hole. I had to get out of there.
Oh, man.
I've broken into the DHU in an attic. They had like a crawl space one in a foamed attic, and I took it apart, got to the electrical, and just put a relay in there.
Yeah.
Where it was always getting powered. I was like using my 24 volts from the air handler next to it that it wasn't ducted into to go through this float switch to energize this relay that if it flipped, the compressor couldn't turn on.
You remind me of a younger version of me, Sean, working on these old commercial systems and just coming up with solutions out of the box. Yeah.
No, you have to.
That's funny.
So,
yeah. Right. What else we got, y'all? Questions, war stories? All right. Well, if no one else has got anything, I think we're going to call it a night then. So Manual D next month, Chris Hughes, talk about the True Flow Grid, duct diagnosis, and Manual D. That's like one of my favorite classes to teach. So hope you guys sign up for that.
Is he going to have a discount code for that True Flow Grid?
Yes, there is. In fact, I'm going to put it in the chat right now. This is not a public discount code. You see the TD 2025? It's only for people that like sign up for my classes. They don't want me pissing off like True Tech Tools and like all the other places. But you get 8% off and free shipping on
That's
that.
nice.
So like I can't post it on social media, but you know.
Is that on their website?
No, like the discount code is not going to be on the website, but when you go, yeah, you have to use their website to purchase it. You can't use it like on True Tech Tools.
Yeah.
You have to purchase it through the energyconservatory.com. But you get 8% off, free shipping, which is essentially what you would get if you bought it off of like True Tech Tools. So like, you know, and I don't get like I could care less whether you use it or not. I don't get anything out of it. They just made it for the Manual D class, and he said you can share it privately with everybody. So this is technically a private room, you know, for people that purchase tickets. So yeah, TD 2025. If it doesn't work, let me know, and I'll message Chris. But yeah,
I'm saving my pennies.
yeah, man, it's but I tell you, it's a game changer. Like once you start using it, and it's so quick to use it, man. I mean, it takes 2 minutes. Especially if you got a media filter at the air handler.
Yeah.
It's just take a reading, slide it out, put the True Flow Grid, or take another reading, spits out airflow, tells you what your airflow and your static pressure will be with your next unit. Like if you're going from a furnace to a heat pump going down inside, it's going to say, yeah, well, your static pressure is going to go up. So, you know, it's really
have you talked to Chris in the last couple weeks about the unreleased forecasting stuff?
No, I haven't.
It is so my buddy was trying to find this particular heat pump, and it was a situation where they have solar panels, they want a 4-ton, load calc is 3.5 ton, and that was a whole ordeal. So we got Chris involved so that smart people can help me because I'm a donkey, and he showed me some of the screenshots of how you can make all the adjustments on the forecasting, and now I already forgot half of it, but it's gonna be awesome. So
well, he is
maybe that'll be coming out in a couple weeks.
I'll ask him about it. He's given sneak peeks before about forecasting, like before forecasting came out officially.
Yeah,
he was talking about it on my Manual D class 2 years ago. So yeah, I'll ask him about it. He'll probably go over it. But all right. Well, thank you again. Recording will come out tomorrow with the email. And appreciate it, y'all. We'll go ahead and stop recording now.
Thank you. Have a good night.